All right, guys. I'm going to go ahead and get started. Welcome, everybody, back to your physics and instrumentation class. It's good to see everybody again, or at least it's good to see everybody's names. Thanks for those that are showing their faces. I love it. Um, so, congratulations, you made it to your last lecture of physics and instrumentation. So this is exciting to be coming to the end of the semester. I also know it's a really busy time for everybody with the holidays coming. So good luck with everything and getting it all done, but this is exciting to be at this point. Just a couple of kind of reminders and business before we get into the lecture. Number one, this class on the syllabus was slated to end on December 4th, to have everything due on December 4th. I went in there and I was actually able to push it to the 13th, which is a Saturday. So I wanted to just try to give you guys extra time so you had a full month from this lecture to finish everything out. So I've been able to do that. The 13th is pushing it to the point where they want me to turn in stuff. And so I just wanted to give you guys as much time as possible. So everything will be due by the 13th. You can have it done by the 4th, sweet, get it out of the way, be done. But I've pushed it out. That's a Saturday. Okay. Now the other thing is I've looked at the tests. It looks like majority of you have been trying to keep up and have taken the tests. Please remember to turn in your test corrections so I can get those done. I haven't seen too many of them come through, so please get those handed in. And then there are a few of you that I haven't seen any tests from. So again, I love to be the non-due date kind of guy because again, I know the life you guys are living right now and how busy it is. But please try to keep up. If there's any of you that are struggling, like there's for some reason you haven't turned in any tests, please reach out to me. We have a month from today, and then there's not anything I can do about it if you don't have your stuff done. So please reach out to me sooner than later so I can try to help you if there's issues with getting tests taken or anything like that. But please get going on those. I'm a little bit of a hypocrite because sometimes I'm a procrastinator too. But please, if you haven't done any of the tests, you really need to get on that and get it done. So, and then for those of you that have kind of kept up, that's great. Keep it up. Keep doing it. So, all right. I think that's about all that I had. This lecture that we're going to do today, we're going to cover PET CT. And so I've tried to kind of PET is obviously something that is kind of taking over nuke med. I'm sure there'll be a day where we do most things on a PET scanner rather than on a gamma camera. And so I tried to kind of stay heavy on PET, CT less so. This lecture isn't going to be meant to, get you ready to take your CT boards. And I also understand there's probably some of you in this group that maybe even already have a CT license. I've had a lot of those come through. So kind of light on CT. We're going to start out talking about PET today. We're going to then kind of in the middle jump into CT and talk about CT for a while and then try to marry the two at the end. And when I marry them at the end, it's mostly in respect to why do we care about CT and what do we get out of CT as nuke med techs, whether that be PET or using our gamma camera. So that's kind of the path we'll try to hit. So let me get my slides pulled up and we'll get going. Okay, someone give me a head nod if you can see my slides. Awesome, thanks. Let me get you guys in a better position here so I can try to pay attention to you. Um, as always, and how we've kind of ran this again, you guys just if you have questions, interrupt me. I'm totally cool. In fact, I love it when you interrupt me because I tend to just yap. So interrupt me, and then also if anybody sees something in the chat that comes along that's pretty good part of the discussion, just let me know. Like if I don't see it, I try to keep it. I've got it on two different screens, so I try to pay attention, but I'm mostly looking at my slides. So don't feel free to interrupt me if somebody puts something in the chat and I'm not answering it or I skip over. So all right, with that, let me get slides back. So again, this is PET. This will be our last lecture for the year. So, and I love PET. PET is a lot of fun. It's what I mostly work with every day. Although in our cardiology department we have a SPECT scanner as well, but we try not to use it if we can. But so this first quote, this is from your Waterstrom book, and I really like this because I think it describes PET well. In a lot of ways, this describes the difference between nuclear medicine and other modalities like CT or MRI and things. But it says the metabolic and biological activities of disease always precede any anatomic evidence of illness. So first, that I love because a lot of other modalities are based on anatomic evidence, right? They take a picture and can see anatomy and you try to figure something out from that. With PET, because it's biological, we're looking at more about the physiology of what's happening, not just the anatomy. And I love how physiology is always going to precede anything that happens anatomically. And so PET allows us to be able to see those processes, which is really cool. So the second half of this is just PET as a biological imaging technique adds characterization of simple molecular processes. So really cool to think about in PET. And like I said, generally in nuke med, it's why we're cooler than other modalities. Don't tell them. All right, so let's get into talking about PET then. How does it work? Where do we start with the basics? First of all, who can remember what beta plus is? Anybody out there want to be brave? What's beta plus? Looking over at you guys. Who's gonna be brave? Maybe I can pick on some of you guys I see at clinicals. Dallin, I'm gonna pick on you, brother. What do you think?
Beta plus is essentially where you have a proton-rich nucleus that emits a positron. Then it travels, and then it will collide another, I believe, an electron.
Yep, keep
And
going.
that will, yep. And then it's an annihilation reaction, so it has to have a certain amount of energy, 511 keV.
Okay, sweet. I think I'm just going to keep Dallin on there and let him go. Like, that was good. It's just the whole slide there. Awesome. Thank you, Dallin. That was great. Yeah, one of the first things he said is positron rich, right? So these are going to be positron rich nuclei. Again, when we're positron, or excuse me, no, I didn't say positron. Just need to listen to Dallin. I'm saying the wrong thing. Proton rich, sorry. Proton rich, right? Which means we have positive charge that needs to go away. Like Dallin said, what happens is that it gives up basically what is a positron. It's basically a positive electron. We term it a positron. That positron, Dallin also said, travels a short distance. That's going to be important. That travel, we're going to talk about, that matters in PET. So it's going to travel a short distance. It's going to find a free electron. And what happens is when it finds that free electron, they form what's called a positronium. We don't hear that much, but they come together almost like their own little unit. It's a very, very brief, just milliseconds of time, but they come together with such force that they have, again, what Dallin termed an annihilation reaction. Okay, annihilation reaction. What does that mean? It means that when those two come and collide with such force, that you have a situation where their mass actually changes to energy, which is a really cool thing in physics. Like, people wondered about this for years. Where can mass turn to energy and can energy turn to mass? That's been like something they've wondered in physics, but this shows that happens. Positron emission, that happens. That pure the mass turns into pure energy, and like Dallin mentioned, it's two 511 keV photons traveling at 180 degrees apart, right? They'll travel exactly opposite directions. Now, when I say exact, the book is going to tell you that it's probably within a variation of about plus or minus like zero point 0.3 degrees. Okay, so almost perfect. It can be a slight variation because of the kinetic energy of when that positronium comes together. But essentially 180 degrees apart, traveling in exactly opposite directions. Now, I will point out to you that on here, it some of these charts that you'll look at will say 0.511 MeV, which is mega electron volts, and then some will say 511 keV. Just understand that when you're looking at that, right? If we go from keV to MeV, it's 3 decimal places or back and forth. So that's all this means. So if you see MeV, it's going to be 0.511. If you see keV, it's going to be 511. We talk in nuke med, we mostly use keV, so I hate that the book does that, but some of the graphics you'll see are like that. But just remember, it's 511 keV, so we're a lot stronger than our like 140 that we use with tech. So just kind of keep that in mind. Okay. All right.
And Michael, you said when they come together, it's a total annihilation, like there's no mass
Yeah,
left over whatsoever.
correct.
Okay.
Their mass actually changes into energy, which again, like that's just cool. Kind of, it's like
Yeah.
crazy. So yeah, you got it. All right. Now, the other thing I need to mention here is those 511 keV photons that are coming out. That is what's imaged in PET, right? So when we call PET, PET stands for positron emission tomography. That's a little bit of a misnomer because we don't actually image positrons, right? The positron only exists for milliseconds of time, and then it's gone, right? So we don't actually image it. What we image is the annihilation reaction and those two 511 keV photons traveling uh, opposite directions. Okay, so just kind of keep that in mind. And I just put this chart up, just a bigger view of what we just talked about, and you can kind of see. Now, I mentioned a minute ago, it's important to understand, and Dallin said this, is that when that when that when that positron leaves the nucleus, it travels a short distance. This travel, the length of travel that happens, is dependent upon the nuclide. So different nuclides are going to kick that little positron off at a greater energy. Okay, it's an excited electron, and it's going to have a little bit further travel. Now, when the annihilation reaction happens, those 511 photons are always 511. Like if we're talking about PET, you never have to worry about, you think about on your spec scanner, you've got your different heads, you've got your high energy, medium energy, low energy, because we're using different KEVs. In PET, it's always 511. If it's not 511, that means it didn't come from annihilation. So when I tell you that the distance it travels is different in energy, that's all I'm talking about, is that little distance, okay, that it travels. And I'm going to connect why that's important in PET here in just a second. But what I want to do is on the next slide, I want to start looking at the different nuclides used in PET and what makes them different and why it matters. Okay, so I've got the book lists common ones. There are other ones that are out there. There's other ones in development, but for the purposes of kind of learning why the differences are important in PET, we're just going to look at these ones that we have here. So what I've got listed here is carbon 11, nitrogen 13, oxygen 15, fluorine 18, and rubidium 82. Okay. So what I want you to notice here, first off, and we'll kind of connect this a little bit, but notice that most PET nuclides that we use have pretty short half-lives. Carbon's got 20 minutes. Nitrogen's got about almost 10-minute half-life, right? F18, which is the one that you guys have probably seen if you've been able to get into it at PET department for oncology, 109 minutes. That's one of the longer ones. Rubidium, which is what we use in cardiology currently, is only 75 seconds. So, I mean, it's really fast. Okay. So those make differences in how we are able to employ these PET nuclides, because you have to be able to have, time to be able to use it, and that affects how things work. For example, thank goodness we have F18 that's 109 minutes, because F18, and we'll kind of mention this later, but it's produced in a cyclotron, and it has to have time to get to you from that cyclotron, right? If it was like rubidium, it was 75 seconds, so we'd be out to lunch. So that's the first thing to kind of notice. The next part of this, when it talks about this range, maximum range and mean range, this is talking about the range of travel of that positron. Okay, how far it travels before it annihilates. I'm not going to focus too much on the maximum range. That's just saying, at a max range, it can do this far. But we're going to talk about this mean. And remember, we talked about mean is just average, right? So this is the average range that they travel. So here's why this matters, okay? And notice, like, for example, carbon, 0.3 millimeters. So it doesn't travel very far. You'll notice that oxygen travels a little farther, 1.5. Rubidium travels pretty far, 2.6. So here's why this matters. And F18 is great, like 0.2. It's really short, okay? I want you to think for a second about, you put a PET imaging nuclide into the body, and let's say that you're using F18, but you're doing oncology, right? So you've got some cancer in there that you're wanting to find. So you put it in, and it goes and it locates within that cancer, right? So where that actual nuclide is sitting is right where the cancer is, but those positrons are being given off, and those positrons are traveling a little bit of way from where the anatomy is, and then having their annihilation reaction. And we image the annihilation reaction. So what that means is that the anatomy is slightly off from where we get the actual image, okay? And so each nuclide actually has an inherent resolution. So when I talk about this, I'm not talking about the camera has a resolution, and we'll talk about that in a minute. But each PET nuclide has a resolution, and the smaller the range of travel, the better the resolution, because it accurately represents where the anatomy is, not just the travel to where the annihilation reaction took place. Now we're talking about millimeters, so it's not very far, but again, each nuclide has an inherent resolution because of that. So if we look at our list again, you'll notice again that F18 is great. It's a really good resolution for PET. It means it's going to represent the annihilation reaction almost exactly where the actual anatomy is occurring. Whereas like something like rubidium in cardiology, it's a little less, it's not as great. Again, we're only talking about 2.6 millimeters, but still it makes a difference in the resolution that we can get from using these nuclides. Any questions on that? Okay. And they're always trying to find new nuclides in PET that have greater resolution, that don't travel as far, that mean range is a little lower. And so there's always things in development, but these are kind of your common ones you see right now. Okay, so production of PET nuclides. When we think about production, what we need to ask ourselves is, Dallin had mentioned earlier that these are proton rich, right? So we need a way to produce proton-rich nuclides. And so what we use is what's called a linear accelerator, or you'll often hear the term, or more common term, is cyclotron, okay? And I'm not going to go over the mechanics of the cyclotron. You'll probably cover that in your pharmaceutical class. But I'll at least mention that the cyclotron provides a way for us to bombard nuclides with protons. They accelerate them at high speed, and a nuclide will be hit with a ton of protons and basically become part of that nuclide and now be proton rich. And so then what's happening is that nuclide is like, okay, now I got to get rid of this. And so in the case of all of the nuclides that we use in PET, it's getting rid of those by that positron emission, okay? Now the only one on here, and I'll go back to this list, the one on here that's an exception, it's not cyclotron produced. All of these are cyclotron produced except for rubidium. Okay, rubidium is actually produced using a generator. So we use strontium 85. So just like your technetium is produced in a generator, it's the same thing. The column is washed, and what comes off is rubidium. So there's a strontium column, and it's washed with saline, and what comes off is rubidium. Okay, so that one is not produced in a cyclotron, and that I could see that being a test question. what,
Hey Michael, I got a quick question for you.
yeah, go
So
for
I
it.
noticed you threw like oxygen and carbon and whatnot on there, but I don't see gallium or copper, and gallium's also generator produced. So are those specific PET nuclides that you're gonna test us on, or was this just a graph you pulled from the book?
It's just a graph I pulled from the book. I do believe I have a question in there that just I was trying to give you a hint to right now that um, in there I list like here's a bunch of nuclides and it's just I only use these ones. And the question I'll just give it to you. The question is which of these was produced in a generator. So but you're right, and there are some more modern ones that are produced. I just took this graphic from the book, and you see some of those as well. So um, I don't believe they mention any of those in the book, but again, like the books are always behind reality. So yeah, thanks for the question. I won't test you. I'll only test you on these ones. Any other questions? Okay. What I want you to understand here is more than anything is that there's that travel, that lower mean ranges produce higher resolution images. Okay. Right. And then again, what else did I want to say here? Oh, the other thing I wanted to mention here is that cyclotrons are usually off-site. Cyclotrons are really expensive. It can be $2 or $3 million for a medical cyclotron. And so because of the short half-lives of a lot of these, you're going to have things that are produced off-site. And so that's one of the things that like I mentioned earlier, that can be difficult with PET is you have to have something that has a long enough half-life to be able to get from a cyclotron to wherever you're at. They are developing some, and nitrogen is one that they're developing right now, that they're using and trying to use in cardiology, where they have a small cyclotron that actually sits on the back of your PET scanner and can actually produce it, kind of on demand. It's fairly high radiation in terms of exposure to text, but those are things that are coming along. Then I was going to also mention the rubidium is produced by a generator, and remember that 75-second half-life is really short, right? So that's not one you can have off-site and bring in, but we have a cart that sits right behind the PET scanner, and you literally hook the patient up to that cart, and that cart washes the column and gives the dose right then. So again, they've found ways to make these work, but that's kind of the challenge is getting things that it's super expensive and we need time to actually be able to use it. What else do I want to mention on here? That I have a note on here again that PET radio tracers were produced according to pharmaceutical good manufacturing practices and the FDA. So they oversee all of that as well, which is kind of inherent in all of the stuff we use in NucMed. So I think that's all I wanted to say for this one. Okay, let's get into talking about how the PET scanner works, how our images are produced. So a PET scanner has a ring of detectors in 360 degrees around the patient. So this is obviously different than your gamma camera. When you use SPECT, you have a head that rotates. In this case, we've got a ring of detectors around the entire patient. The other thing to think about with PET versus just generally using a gamma camera is that we always image in the axial view. That's the same thing with CT, with MRI. You're always imaging in the axial view, and then you're always reconstructing images. So you really don't have, like spot images and things like that with PET, like you would with regular gamma camera. Everything's in the axial view, so that changes a little bit how we do things. And the other thing is that you're acquiring all of your data all at once instead of gathering in steps for a reconstruction. Data is gathered all at once, and we'll talk about how this works and what the reconstruction looks like and things like that. So PET uses scintillation crystals just like SPECT. These crystals are a little different. They have to have certain qualities to be able to work for PET. And I've listed some of those right here. So the first thing I've got listed here is that they have to be high density because they have to be able to stop a 511 keV photon. Remember when we talked about SPECT, we talked about the importance of the photoelectric effect, right? You have to be able to stop the photon and completely absorb it to be able to measure it. So with 140 keV, we can use the type of crystals that we do there, but with 511 keV, we've got to change our crystal type. We have to have something a little more dense. And so that's what we're going to look at on our next slide. We have to have efficient conversion of photon energy to light energy, just like we've talked about with SPECT. We need to produce large amount of light quickly, and we have to have a fast decay time. And we're gonna talk about that. Decay time here is going to be really important because of how we image. Most crystals lack one of these. You know, there's no perfect crystal out there, but they're constantly trying to find newer and better ones. Here's the common ones that I have listed. And so with this chart, let me kind of show you how this chart works. So we've got the sodium iodide is the first one listed. And so that's our gamma camera, what we have in our gamma camera, what we've already talked about. And we're gonna talk about the density and the atomic number, emission intensity, which is the light given off, and then decay time, which means how fast does it produce light and then go away again so that it can produce another light, right? And so what it's doing, and it mentions it right here, is it's doing everything kind of relative to sodium iodide that we use, the thallium activated sodium iodide, right? And so, for example, let's go up here first and just look at density. So the density of sodium iodide is 3.7. And again, that works because we use 140 keV and, you know, things in that range. You'll notice that BGO is one of the first ones that they used for PET. It was kind of the first go. And I've listed, by the way, guys, I've listed BGO, GSO, LSO, LYSO. Those are all down here. Bismuth germanate, gadolinium, orthosilicate. Anyway, I'm not going to use those names. I'm not going to butcher those. And in a PET situation, when you're at a clinical, you're never going to hear anybody use those full names. Even if you may not even hear them use the short name, but if they do, they'll just refer to it LSO, LYSO. So I'm just going to save you my slaughtering of that and just do that. So BGO is kind of their first try. You'll notice that the density is quite a bit higher, which is great, right? So now we can stop those 511 photons. Atomic number, obviously that speaks to that density, right? So you have a lot more dense. But what you'll notice here is with the BGO crystal, relative to thallium, if thallium was 100, sorry, not thallium, sodium iodide, thallium doped sodium iodide, but the BGO was only 15. So the light emission wasn't great, okay? So they were able to stop the photon, which we absolutely had to have, but light being produced, not wonderful. You'll also notice the decay time. So this is the crystal lit up and it's able to go dark and be ready for another event. Is down to 300. And this is nanoseconds. And I want to point that out because this is very, very quick. In fact, just to give you a grip on this, and this is going to matter in a minute when we talk about imaging, nano, remember, means billion. Okay, so you're taking 1 second and you're dividing it into 1 billion parts. So these times are very fast, right? They're extremely fast. But again, we want to get down to the lowest. So here with BGO, we are 300. So again, we not as good as sodium iodide. And then hygroscopic is just the sodium iodide. We talked about this, and I guarantee on your boards you'll have this question, but sodium iodide is hygroscopic, which means it's water loving or water absorbing. It will absorb water out of the air. The nice thing about all these PET crystals, none of them do that. So that's an advantage. So you can kind of see BGO wasn't great. It worked, like you could get PET images from it, but not the greatest thing in the world compared to sodium iodide. After that, they started coming up with the GSO, LSO, and LYSO. So on the GSO, you'll notice not as great a density, but still good enough to stop the 511. You'll notice our light emission came up, so that's good. We need that high light emission. The real, advancement here was that you came down to 30 to 45 nanoseconds. So you cut it clear down to like 10% of what it was before. So now we can get events, shut them off, record them, be really quick with it. Okay. Then they started coming with the LSO, LYSO. These are actually super similar. You'll notice they're both 7.4 in their density. So again, really good for able to stop the 511. And that's represented in their atomic number 2. light emission started to come up. So now we're 75 and 80. So we're quite a bit better. And then again, 40 nanoseconds. So these two are probably what you'll see in any PET scanner you have today. Most the BGO and GSO are kind of in those first PET scanners that they came up with. LSO and LYSO are kind of what's in everything. We have two cameras in our cardiac department, and they're both LYSO now. We had one that we replaced, what was it, a year ago, 2 years ago, that had LSO crystals, but now they both have the LYSO. Okay, so that's kind of your difference in the crystals that can be used. And again, the important thing to understand here is, again, we've got to stop that 511 photon. We need really good decay time, and we'll talk about why that's important in a minute here. And we need good light. And so again, with the crystals they have, they do a pretty good job. All right. So I'm going to talk about kind of the design of the scintillation crystals and how they work. I've got this slide for you guys, but I'm actually going to go to the next slide because it's a graphic. And so you guys can go back. I'll basically say everything on this slide while we look at the graphic. It's just easier to talk about when we can see a picture. So I'll skip past here and I'll leave that. You guys have that slide for all the information. Okay, so detectors are configured as rectangular cube-shaped crystals, and they're about 3 to 4 millimeters wide, 10 to 30 millimeters long, and that can vary somewhat, so don't get too crazy with it. The one thing I want you to know for sure is they're 3 to 4 millimeters wide. Now, when I say that, I'm not talking about this entire crystal head. And there were two designs that they came up with. Mostly they look at this design that's on graphic B. I think most of them are this way now, but originally what they did is they took a crystal and they cut slices down the crystal. And those are your 3 or 4 millimeter kind of sections. Okay, so each of those are 3 to 4 millimeters. And what they're trying to do, and then you've got photomultiplier tubes on the back. And so this works somewhat similar to your SPECT scanner. The one thing I want you to kind of disassociate is that with the SPECT scanner, the crystal is one large crystal across the entire head with multiple photomultiplier tubes. What they've done in PET is they've tried to break those crystals up into just their 3 millimeter sections. The spatial resolution of a PET scanner is determined primarily by the size of the crystal. Okay, so when we say that there's 3 or 4 millimeters, that's the resolution of your SPECT scanner. Now, if you remember back to PET, normal PET images, when you do like a spot image, that's going to have a similar resolution. It's about 3 or 4 millimeters. But when you do a SPECT image with your gamma camera, then you go up to something like 12 millimeter resolution. So when we look at reconstructed images on SPECT, we're at around 12, whereas when we look at reconstructed images on PET, we're around 3 to 4, and that's primarily determined by the size of these crystals. So initially, they kind of cut lines to try to have one crystal kind of see most of the light and locate it that way. And then later on, they actually separated them out completely, and then they put reflective material in between to even increase the light intensity in each one of those cut crystals. Okay, now these are what we call blocks. So this section, rectangular section of detectors with about four photomultiplier tubes on the back is called a block. Sometimes they're called a bucket, but it's called a block. And blocks are going to be set up and arranged all around the tube. And we'll show you that in a second. Let me hurry and show you this. So this is actual crystals. This is what they actually look like. And these are 3 millimeter crystals that you're looking at here. So they're actually blown up a little bit. They look a little bigger on this graphic than they are because, again, this only represents 3 millimeters here. Okay, so that's what they look like. You have these blocks of crystals, and then you're going to have photomultiplier tubes behind that. But they take those buckets or those blocks and they arrange them in rings all the way around the detector. And so you typically have, depending on the size of your detector, your field of view, 18 to 40 or even more consecutive rings of crystals around the patient, okay, that are going in. And that's what creates your entire field of view along the long axis. So you can see that they've got it right here. Again, sometimes we'll call these modules, buckets. There's a couple of different names for them, but this right here represents one slice through here. So what you're seeing right here is this makes it look like there's 3 PMTs on the back of each of these crystal sets. Each one of these boxes is the 4 PMTs. So there's 4 here, 4 here, 4 here. So each one of these guys is one of these guys. Okay, so graphics aren't the best. I don't love that, but that's what these are. Okay, and so each one of those represents a ring around the detectors. All right, now we need to talk about, we need to wrap our mind around a different way of looking at how we gather images. And we're going to talk about what's called coincidence detection. And I'm going to leave this slide and go to the next slide. But this is kind of what we'll mention on the next slide. So I'll leave that for you guys. But things happen a little different in PET. So remember, you've got a ring of detectors around the bore of the gantry. And PET uses what's called coincidence detection, okay? Sometimes it's referred to as electronic collimation. And so what you have happening is right here on this one, and I won't focus too much on this graphic on the right now, but let's say you've got your patient in here and you have an annihilation reaction that happens right here where it has this little dot, okay? And remember, what happens is you're gonna have a 511 traveling in opposite directions, and so that's what this line represents. You have a 511 that goes over here to the left of the patient, a 511 that goes over to the right of the patient, okay? In your camera, they have set up what's called a coincidence timing window, okay? So these detectors are gonna both see that event that took place, and there's a preset timing window of 4 to 12 nanoseconds in which it will accept an event. What the camera looks for is events happening at the exact same time on both sides of the detector. And so if an event happens at the exact same time on both sides of the detector, it's going to record that as an event that happens. Now, when I say the exact same time, I'm talking about within that 4 to 12 nanosecond timing, okay? Remember, nano means billion. So this is tiny little quick things. This is why we need crystals that can light up and go away quick, okay? We need that decay time to be fast because they need to be able to see these within a short, tiny amount of time. If it sees 2 events on opposite sides of the detector, what it's going to do is form what's called a line of response. And that's what this represents here, this line of response. And what the camera is saying is, camera's saying, I'm not sure, all I can see is that I had an event recognized here and I had an event recognized on the other side of the camera. And I'm not sure where it's occurred yet, but I'm going to make what's called a line of response. And it's going to record the intensity of that interaction and the fact that it took place somewhere along this line. So it forms a line of response. Now, sometimes we call this, people will call this electronic collimation. And so this is one of the ideas I have to try to wrap your mind around. So let me ask you this way. Let me ask you guys a couple of questions. When we think about gamma camera, or even you can think about this as your collimators in X-ray, what does a collimator do? If you were to say, what's the main purpose of a collimator, what does it do? Let me ask you guys that. Somebody answer that question.
Determine
unwanted. Oh, sorry, Ashley.
Yes, participation. I love it. I don't know who talked first, but Ashley, go ahead. Tori, you too. Well, but Ashley, go first.
Okay. It mainly determines the field of view that you take an image of.
That's true, especially with X-ray. That would be true. With gamma camera, though, it doesn't necessarily determine the field of view. It does some other things. Tori, what do you got to add to that?
I was just going to add that it eliminates the unwanted whatever photons or imaging data sets.
Yeah, yes, this is good. Both of those are great answers and true, but that's what I was looking for. It eliminates unwanted photons. Again, With your X-ray collimator, and you comb things down to where you're wanting X-rays to go on your patient. So it does determine the field of view on an X-ray. But what it's originally doing is saying, I don't want these photons to hit my patient. So you're collimating out unwanted photons. In a gamma camera, that's certainly true, right? Because we've got gamma rays flying in every which direction. And what we say is we only want parallel ones. And so we're cutting out the ones we don't want. So again, we're getting rid of unwanted photons. So here we're doing the same thing, but it's called electronic collimation because you have to think of the collimator as that timing window. It's not a physical collimator that we adjust in X-ray. It's not a collimator that sits there and blocks. But what we are still doing is saying, I don't want any photons accepted unless they do two things. One, happen 180 degrees apart, and two, happen within the 4 to 12 nanosecond window. If it's past 12 seconds, collimated, it's out. If it's before 12 seconds, collimated, out. It has to happen within that 4 to 12 nanoseconds, okay? So that's what we mean by it's electronic collimation. So coincidence detection, collimated within that short timing window, okay? And what it will do then is it will just form a line of response. At this point, all I'm telling you is that your camera knows something happened along that 180-degree line. That's all it knows. Doesn't know where it took place, just knows it happened, okay? Any questions on those two kind of principles so far? We'll build on those. Don't see anything, nothing in the chat. Okay, good. All right. So you have a couple of things that happen within that timing window, and here's where we'll explain the timing window and why it matters and how it works. And again, I'll leave this information here for you guys, and we're going to go to the next slide. There's something I want you to ignore for a minute. We're going to talk about the difference between a 2D scanner and a 3D scanner. So for a minute, you'll notice that there's septa right here. Ignore those because I haven't told you there's septa yet. We're only going to mention them once for 2D scanners, which aren't made anymore. So I don't love this graphic for that. So don't worry about the septa idea. But what we're going to talk about is a couple of different kind of events that the camera will see that can happen within the PET scanner. So the first thing I want to talk about is what we will call a true count, okay? And a true count is when an annihilation reaction happens, they travel 180 degrees apart, the two detectors on opposite sides catch them, it sees them, it's within that 4 to 12, it's within that timing window, and it records a line of response as a true event, okay? The other thing that can happen, and we call that a true count. We call that a true count. The next one we call a random count. And what a random count can be is that two separate annihilations can happen, and that's actually this one over here, this graphic C. Two separate annihilation events happen. So you've got one happening over here on the right side of the patient, one over here on the left side of the patient, and it's traveling at the opposite angles, but it happens 180 degrees apart. So the camera sees it and questions, okay, is this a line of response? Okay, and so we can have these random counts, and there's nothing you can do about that. Those random counts will happen. I'll talk to you in a minute about how we correct for that. But sometimes that's going to happen. As you imagine, there's stuff going everywhere, right? And so you're going to have some events that appear to be a line of response, and those are called random counts. Those are kind of your two main things. The other thing that can happen, and this graphic is really exaggerated, but you can have an event happen, and the two 180-degree annihilation events, they go in opposite direction, but one of them, because of anatomy or something else, has a slight turn off of its course. And this would be essentially scatter, and we call it scatter. This is how scatter can happen in PET. The reason I don't like this graphic in the middle is that it's super exaggerated. Remember, I told you before that the events have to happen 180 degrees apart with a variation of like 0.3 or something like that, right? So this is getting past that variation of 0.3, so maybe 0.4, 0.5. I don't want you to think that a 511 photon comes in and takes like some massive turn because it hits a dense bone. That's not what happens. We're talking about just enough that it doesn't happen quite 180 degrees apart. And so in this case, the camera will see it at these two locations here instead of exactly where it occurred. And so there can be these inherent things, and scatter is an issue, and those random counts can be an issue. Now, what you're seeing here, and we'll reference this later. If you had your donut here and you cut your donut in half, and then you turn and look down it on the side, that's what these graphics are representing. And so it's just another way for you to kind of see how things are occurring in here. Again, ignore the septa. We'll talk about that in a minute, but it's not going to happen that much. Okay. So what I want to mention on here, again, when you look at that, you have these true counts and then you have these random counts. The question then becomes, well, how does the camera delineate then between what's a true count and what's a random count? And what the camera will do is, remember, I said that the timing window is 4 to 12 nanoseconds. So it's saying everything within that 4 to 12 nanoseconds is a true event. Anything outside of the 12 is a false event. So what you can do in that case, and maybe I should mention this too. I was going to mention it later when we talk about what's called time of flight. But the principle to think about here is that your camera, the circumference or the diameter of this gamma camera, it's fixed, right? It doesn't change. What that means is that your camera knows where its dead center is. And when we think about the travel of gamma rays, when we think about it, gamma rays are simply just light, right? Remember when we went back to a graphic that I showed you a couple times where it shows, it shows light, radio waves, the different kind of waves, all the way up to gamma waves and how they get increasingly more energetic, right? Well, our eyes are attuned to be able to see light. Our cameras are attuned to be able to see gamma, but they're still just energy, correct? And so the question I would ask you guys is, how fast do you think a gamma photon travels? If you think about the fact that it's just energy, if you were to throw out a guess, how fast do you think it travels?
Speed of light,
Doesn't it
right?
travel at the speed of light?
Oh, who said it? Yeah, yes, exactly. Right? So if we know how big our camera is, we know where center is, and we know that a gamma photon is going to travel at the speed of light, that's where we get that 4 to 12 nanosecond window. Is the camera knows that if it's past 12 nanoseconds, my gantry is such a size that if it's past 12, it definitely didn't come, it came from something else, right? And so that's where you get that window. And so in the case of these random events that still happen, what the camera will do is it gathers all the data. So it will take any lines of response that it saw that were past 12, and it will use those as a subtraction map. And it will say, well, I know everything that happened after 12 is false and fake. So if I take where those lines of response are, and I put it back on my 4 to 12 nanosecond window and subtract anything that matches out, that's how they get rid of and only come to those true counts. But it's why we look at true counts and random counts, because we're going to need to know what happened after 12 nanoseconds so we can compare it back to our normal counts and subtract that data out and only leave the anatomy that matches up with that 4 to 12 second timing window. So that's how it's done. I'm not necessarily going to test you on that, but the idea is important to understand. That's why that timing window works, is that we know how big the gantry is, we know how fast those gamma events can travel, and so there's only a certain amount of time that could actually even take place within that fixed circumference of the gantry. Okay. What else do I want to put in here? I think that's about it. We'll mention a couple other things that we'll tie on later slides, but we'll move on for now. Okay, so I want to talk about moving on to that's the general idea of how we get those we're getting data. So we're going to start talking now about how the camera reconstructs the data. Okay, I brought this up here just to remind you that we're going to use filtered back projection and iterative reconstruction in a very similar way to how the gamma camera worked. And I know I love to show you this graphic. I think I've showed you it on at least one other one, but this is great to understand. So I want you to think again about back to how filtered back projection works, how iterative reconstruction works. I'm gonna play this video real quick, and I know this seems tedious and like we're just repeating stuff. But I want this fresh in your mind because I'm going to compare it directly to how PET works. Understanding how SPECT works is going to help your brain be able to say, oh, okay, I see what the PET is doing now. So I'm going to play this video. You guys have seen it before. First, it's going to be the acquisition on your gamma camera. And so again, we're going to have our object here. As your gamma camera travels around, it gets projections at every angle as it travels, and it forms a sinogram. Remember, there's sinograms for every projection. And so that's what you see here first. So here represents our camera going around the patient. It's seeing all the different intensities, and it's putting those intensities into a sinogram. Okay, so that's the gathering of the data. And now we're going to look at the reconstruction of the data. Remember, we talked about how it's going to take each projection and cast it across the matrix. I'm going to pause right here. This is important to understand. Remember, this projection is it saw one projection through the body, one angle through the body, and it just sees the intensity values, right? It just says, I know somewhere along this path is this much intensity as it went through the body. And so I'm going to throw that intensity across the entire matrix, okay? Remember this image here for what we talk about in PET for a minute. Everything's going to be thrown across the matrix. And again, then we're on a gamma camera, we're going to gather multiple angles, throw them across the matrix. Where areas of activity intersect, higher areas of activity intersect, it's going to form higher areas of activity on the image. Where lower areas of activity intersect, it's going to form lower activities of area, okay? So that's reconstructing the image from that sinogram, okay? I won't go over iterative right now, other than remember it's a mathematical process. We'll talk about that in a minute. I really wanted to show you that image of everything being cast across the matrix, because now we're going to compare that to how it works in PET, and it's very similar, okay? So remember that I mentioned a minute ago that we get this line of response. And remember, the camera at this point doesn't know where it occurred. It only sees that there was a 180 within the timing window. And so it says, fine, I see this response. I see something right along this area. So it forms this line of response. Now, in this case, in this graphic so far, we've only looked at one line of response. However, if you think about it, if the event is happening right here within the anatomy, you've got 511s that are opposite direction going everywhere, right? They're going every which way. So that means that there was a line of response here, but there was also one that happened up here that was parallel to this line of response within the anatomy. And you had another one that happened here and here and here. And so what the camera does is it's going to look within the lines of response that it sees, and it's going to say, I'm looking for parallel lines of response, okay? And so I'm going to record all the parallel lines of response. And this is exactly like your gamma camera seeing the intensities that it casts across the matrix. So what it does is this graphic down here, much like a gamma camera, we would put the gamma camera here, we would require, then we would go over here, then we would require, then we'd go here and acquire. And then again, we would put those intensities together across the matrix, right? Well, the same thing is happening in PET. It's just these lines of response. And remember, instead of our camera moving and gathering these separately, it's gathering all lines of response all at the same time. But the camera can recognize a parallel response that is parallel with another response, okay? And so it forms the same type of images. Again, here's another explanation that compares to. Here's SPECT, right? So it gathered these two angles, and it's going to throw both of these angles across the matrix. PET's going to do the same thing. It gathered parallel lines of response here, parallel lines of response here, and it will also throw them across the matrix as it reconstructs in the exact same way. Okay? So the reconstruction happens the same way. So, and I kind of listed that here. PET data acquisition stores projection from lines of response in sinograms. Each sinogram represents one slice, just like on PET. And then each horizontal row in a sinogram represents a count or the projection across the distance of the gantry. And the vertical axis of the sinogram is the angle from which the projection is taken over 180 degrees. So again, just wherever those lines of response are, it's just like if we had a moving camera, like a spec camera, but we're requiring it all at once. Okay. And in the very same way, now this is a spec image, but it works the same way, right? So a sinogram is built by getting a projection here that goes on the top, the next projection here, the next projection here, the next projection, and all the way around. And so you form a sinogram based on that 180-degree projection, okay? And then this sinogram, again, is used to reconstruct the images that you're going to look at. So same thing as PET or SPECT. So if you kind of understand how SPECT works in as far as reconstruction, the only difference is, again, we're looking at lines of response that match each other, that are parallel to one another, okay? Questions on that? I saw somebody's, wait. Maybe you're, okay. I thought I saw someone talking, but if you're trying to talk right now, you're muted. I thought I saw somebody. Okay. All right. If they're not questions, we'll move on, but that's kind of your general idea. Okay. I will tell you, when I was learning this, it took me a minute to wrap my head around it. So, read what's in the book on this same topic, look at these slides again, and try to make sense out of that. Okay. Again, I mentioned a minute ago, we use filter back projection, and we also use iterative. Now, filter back projection will work exactly the same way. Iterative also would work the same way. There are there's a few different iterative types of algorithms that are used in PET. It mentions these in your book. It mentions these three. So I thought I would kind of go over them. To be honest with you, I would be a little surprised if these were on your boards, but I will tell you that the review book that we use on our summer semester, where you go through a bunch of tests, I know that there have been a couple of questions in the review book on these. So again, I would read over these in the book. I'll give you kind of a brief explanation, but they're all iterative reconstructions. And just remember that iterative is based on a math approach. It will take the projections and it will look at one projection and guess what the next projection should look like. And then it'll take that guess, look at the second projection. If it's wrong, it will adjust. And again, it mathematically does that in multiple iterations until it can figure out the exact where everything should be placed on the matrix. Remember how I talked about last time that the advantage with iterative is that you're going to have a lot less that you have to filter out, because we're not just throwing everything across the matrix. We're actually looking and placing things exactly where they should be and getting rid of all the extra stuff, right? So you can get some better images. I also talked about how it requires a lot of computer and it requires a lot of time to make reconstructions. And so that's kind of those disadvantages and advantages. Again, they're the same as what we covered when we looked at spec. But let me cover these three, what the difference is briefly. They're actually all really similar, but I'll cover kind of those three briefly, and then I would look at them in your book. But MLEM, what it does is it uses it'll take like 20 to 30 iterations. So it doesn't just over and over and over iterations. It'll do a limited number of iterations, and it will use all of the projection data. So it's almost like a mix between iterative and filtered back, and kind of maybe more heavy on using the filtered back projection than on using the iterative. And so the advantage you get with that is that less math, so less computer time, less time to reconstruct. But again, you might still have some of the back projection issues with the filtering and things like that. So it's kind of a mix. Then you have ordered subset expectation minimization. It will use just a small subset of the projection data, and then try to use iterative and limited number of iterations. So it's kind of the opposite of MLEM, which OSEM is heavy on the side of using projection data, or excuse me, on using, let me make sure I don't tell you that backwards. So it uses a small amount of projection data and goes more towards the iterative side, the math side, whereas the MLEM will go small on the math side and longer on the projection side to produce its image. It's kind of, so they're kind of option. And again, so what that means is that OSEM is going to have, because it's a limited number of the math of the iterations, it's a little faster, a little more efficient. And then Ramela is a vendor specific, and I don't even remember, I'm not sure which vendor it is, but if you read through the book, it will talk about, it's a specific algorithm that vendors use. That's all I could really find. I don't think the book even mentions a lot about it. So that's why I said I would hope that you don't have actual test questions on your board that aren't even mentioned in the book, but they do talk about these just very briefly. Understand that most algorithms like this are just some sort of combination of iterative and filtered back. And I would tell you too, there's actually even more than this that start getting vendor specific. So again, I highly doubt you're tested on that, but I do remember 1 or 2 questions on the review book. So I'll kind of leave that for what it is. But I definitely would understand that these different algorithms and how they use filtered back and how they use iterative and what the difference is. Any questions on that? Sorry, I know that's kind of muddy, but I'm trying to give you the best thing I can with what the book gives and what I've seen on some of these tests. So, okay. All right, so now the other thing we need to talk about with PET is time of flight, okay? And I'm gonna leave this here for you to look at, and I'm gonna go to the next slide so that I can look at a picture. It's just, again, I don't know why, but with PET, pictures are easier for me. So we're gonna go to the picture. Okay, so this is where it was in a graphic earlier. Time of flight is something that came a little later as PET continued to develop. As cameras got faster and as crystals got better. So time of flight wasn't available on some of the early ones like the GSO, where the crystal wasn't very fast. But when the crystals started getting fast and could really get these nanoseconds of time, we started to be able to get this time of flight. So let me kind of try to give you what this refers to. And this will go back to our discussion about the gantry size, the fact that we know things are traveling at the speed that they're traveling at. So what I want to show you here again is with the line of response that we mentioned earlier, all we said is that, hey, there's a line of response here, right? The camera sees it. It's within that 4 to 12 nanosecond range, all right? As the crystals got faster, what this allowed to happen is, again, this first one represents, so this kind of circle in the middle, that's your anatomy, that's your body part, right? And so we had an event happen over here on the left side of the patient. And obviously they both traveled in 180 degrees apart. What time of flight allows is it allows the camera to look at exactly when the event, if it was within the timing window, when did that event take place compared to what the camera should expect to see taking place if the event were to have happened exactly in the center of the gantry, okay? So what I mean is that if this event, instead of taking over here to the left of the patient, would have happened dead center in the gantry, because the camera knows the length in centimeters from the center of the gantry to the edge, it can then take and calculate that speed of light, and it knows exactly how long something should take from the center. And so it compares this event that it sees to what it should expect from the center. And in that sense, it can then adjust, meaning that this detector over here saw this at a certain time that was shorter than expected from center. And this detector over here saw the event happen in a longer time than expected, still within the timing window, okay? And so what it does is those two that saw that line of response, they compare their times and say, okay, we can guesstimate then, based on our times, that this event happened somewhere right about here on the line of response. And it does that, it can guesstimate or calculate within about 9 centimeters, okay? So that's what this is representing is, now instead of having a line of response that goes across the entire camera, you now have a line of response that's only 9 centimeters long. Now, this one over here represents more of the statistical data and the likelihood. And so the camera is able to look at that and say, okay, based on our timing window, it's most likely that it happened here, and here's my statistical differences. It's just representing it in a different way. But essentially what you should know is that within that 9 centimeters, the camera knows it happened. Now, why would that be an advantage? The reason it's an advantage, especially when you think of filtered back projection, is instead of taking a line of response and casting the entire thing across the matrix and then having to filter everything out, it's only going to cast the line of response across the matrix in a 9 centimeter section for that event. So for this particular event, obviously you'd have events happening all over the place, but it's all going to be within that 9 centimeters from where the event took place, which means your reconstruction time is really, really brought down because all you're worried about is the data that happened within that 9 centimeters, okay? So again, brings the speed of reconstructions and all that way down and can kind of guesstimate where that happened. And so you get some improved imaging because of time of flight, and you can also get improved reconstruction time in terms of patient throughput with time of flight. I would dare say that your cameras today, anything that's probably within about the last 5 years at least, could be even longer than 5 years, but at least the last 5 years, you're going to have time of flight on your PET. That's with the type of crystals that are in the camera now, time of flight is possible. It's going to be your older cameras that don't have time of flight. Okay. And so time of flight's really awesome. We actually had, this was a few years back when we had our 2 cameras. Our newest camera at the time had time of flight, and then we had a camera that did not have time of flight. And we had done a patient, he was a kind of a large guy on the camera that did not have time of flight. And our images came out kind of crummy. We couldn't figure out what it was. We tried every trick in the book that we know in cardiology to reconstruct or to make these images better. And for some reason, they just didn't come out good. And I think it's because he was such a large guy, the camera just had a hard time with the reconstructions. So what they decided to do is just kind of read that test as non-diagnostic and to have the patient come back. When the patient came back, we're like, let's get him on the camera with time of flight and see if that makes a difference. And we took images there, and the images were way, way better because again, with such a large patient and when it tried to reconstruct all that data, it was just having a struggle. But when we used the time of flight and it brought it down to a much smaller data set, got to ignore half of what was going on in the camera from that patient's body, it made a huge difference. So time of flight is a kind of a cool thing that's developed and a cool advantage. And again, only possible because we have those better crystals like the LYSO that have the ability to have tiny nanosecond recordings. So, okay. So that's time of flight. Now we'll talk really quick about 2 and 3D scanners, and then we might take a quick little break, we'll see, and get into some CT stuff. So again, I'm going to leave this information here, and we're going to go over to the next slide. The difference between 2D and 3D. So when PET was first introduced, it was introduced with 2D scanners, and they actually did include SEPTA. This is why I kind of saved this to the end, because all of your scanners now are going to be 3D scanners that have no SEPTA. But they originally had SEPTA. And remember, this was on those old BGO crystals. And so the crystals weren't very fast. And so they put SEPTA in here to try to limit what was being seen just to kind of each detector bucket, so that they could kind of limit it to only that and not have so much overwhelming the system and being seen. Because remember, you had to have light response and then decay, light response, decay to get another event. And so without the SEPTA on a 2D scanner, the system would get overwhelmed, and it just wasn't able to record those lines of response without some SEPTA in there. So again, not really necessarily like the SEPTA in the on a gamma camera. That one actually helps us form our image. This one was more about kind of just reducing what the camera had to see all at once, so that the crystal could handle it. Okay. Later cameras are now 3D. They've taken off the SEPTA. The cameras can handle it because there's those nanosecond times are down to really low, and they can I don't want to say refresh, that's a bad word, but they're ready to receive a count quicker, right? Now, the other really cool thing about this is that the data gathering and the sensitivity goes way up. And the reason is that over here, you pretty much could have a line of response that went exactly across the camera. And again, what we're looking at here is the donut cut in half, right? If we cut half the donut and then looked down the donut this way, and so your z-axis is through, the patient travels through the camera this way, right? So with this one, all you could do is see what's across these two septa to form line of responses. On a 3D camera, it can form lines of response across the entire field of view. So instead of just having an event happens here on this one and having an event happen 180 degrees on the one opposite side of the detector, exactly opposite, you can have an event that happens clear over here on this detector, and it sees that line of response over on this side of the opposite side of the camera, and that can form a line of response, which means that your sensitivity, what you're seeing all at once, went way, way higher, right? So you're gathering so much data, and it's so sensitive that it really went up. The sensitivity of being able to see all of the events happening from a 2D to a 3D scanner went up by like a factor of 5 to 10. It went up high, and allows us to see so much more and gather so much more. Also, you can gather the data a lot faster because you're getting lines of response from everywhere. So significant improvement in sensitivity, quality. The one downside here is that you're going to have more opportunity for some of that scatter and random events. But again, because of those nanosecond timing windows, we can subtract out anything past 12 and resolve that and make up for it. And so the 3D scanners are just pretty cool, how they're able to function and work. But that's the difference between a 2D and a 3D scanner. So if you were to get a question like that, 2D has septa, 3D much higher sensitivity, no septa, is able to gather lines of response from any angle within the detector. And I thought this was a good time talking about that as well, to kind of bring up the differences between PET and SPECT. And I've kind of sort of mentioned some of these as we went through, but these are just good points to hit. But remember that the spatial resolution of PET scanners is determined by the size of the crystal. It's significantly higher in SPECT, and I mentioned this earlier, but about by 4 times. When we compare PET to SPECT, we're talking about 4 millimeters versus 12. So much, much better images. Your count rate capability to gather data, it goes way up. And again, we talked about earlier, I actually think this, I may have put the wrong thing on here, because I think the gamma camera efficiency or the sensitivity is more like 0.1%. I'll have to look at that. I've not noticed that was at 1. But the PET count rate gets up to in the near 2%. And I actually think that this number is from the book. And I think this number is actually for a 2D scanner. I think a 3D scanner, that the rate efficiency is even higher. So again, the efficiency of the camera, the sensitivity of the camera is way higher. The resolution is way higher. And you just get much better quality images. Because of this, in cardiology, it's to the point, like I said, we have 2 PET scanners and we have a gamma camera. And usually we're only putting people on the gamma camera for a cardiac SPECT when the insurance, it really comes down to an insurance thing. Like the insurance won't pay for a PET for some reason. They'll pay for a SPECT, even though the difference is just it's a couple $100 or something like that. The insurance companies haven't got on yet. But we always feel like we're doing a disservice to our patient if we have PET available and we're only doing a SPECT because of this, because we get such better images on a PET scanner with just much, much better resolution. So again, PET's the way to go if that's a possibility. But
hey, Michael, was it you or perhaps another teacher who'd mentioned that it looked like Medicare or Medicaid was going to actually start covering the PET cardiac scans?
Yeah, it could have been me that mentioned it. I don't remember if I did, but yeah, that is true. We've heard that it's on its way, but it hasn't happened yet. But yeah, supposedly that's coming. When that comes, that's probably going to make a big difference. You're probably going to see a lot less cardiac being performed on SPECT. So I hope so, because really it's if PET's available, it's a disservice to do a SPECT on your patient because it's just such a better image. So. Yeah. Did I tell you guys? I can't remember if I was telling you. I think I mentioned this. I can't remember if it was this group or not. But in our facility in Intermountain, we actually did a comparison, and we took our PET versus our SPECT over a few year period. And basically we looked at anyone that had a positive stress test and then went up to cath and indeed found that yes, the stress test predicted the cath and it was correct, right? And the number with SPECT was somewhere around like 60 to 65%, that when we had a positive test on SPECT, we went up to cath and indeed, yes, there was an issue. With PET, that we did that same study, and again, this is internal data, but we did that same study and we went somewhere up to close to 96% with PET. That when PET showed that there was something, indeed, we went up to cath and there was. I mean, that's a huge difference. I mean, I don't even think these two numbers don't really even speak to that kind of difference, but that was pretty huge for us. So, all right. We're at 10:15. Let's see. Why don't we do a quick, just 5-minute break? Let people use the restroom real quick, and then when we get back, what we'll do is we'll try to cover CT in a little bit faster manner, and I don't have as much, and then we'll tie the two together and try to be done on time. Okay? So take 5. Come back at 10:20. All right, guys, let's go ahead and get started. See if we can try to get this done on time. As I've mentioned before, if I go over a little, you guys are welcome to just ditch, and I'll keep recording, and we'll finish it out. But I'll try and be fast because I got to go to work too. Okay, so I've got a picture of PET CT here. In most scanners, what you'll see is the CT is going to be contained on the front of the gantry, and the PET's going to be contained on the back side of the gantry. Kind of two things that are really advantageous with CT when it comes to PET are two purposes, and we'll kind of reference this as we go along. But one of them is that it's going to help us see anatomy, where our activity is located within the anatomy. That's really important, especially like oncology is super important. The other thing it's going to provide is attenuation correction, and we'll talk about what that is in both of those things. But those are kind of our two kickbacks to CT. So with CT here, I'm going to try to kind of do, I'll be quick with a lot of this and try not to yap as much as I do with PET. Because like I said, CT matters, but not to the point where we need to get you guys certified from this class. So two things I want to kind of understand, this is going to matter as we go along and talk about how CT helps us, is that PET is what we call emission data. What I mean by that is that we've made a body part radioactive, and it's emitting photons, it's emitting gamma rays, and we're gathering that emission from our camera, so it's emission data. CT is transmission data, which means that we shoot X-rays through the body. Higher density parts in the body attenuate or stop those CTs more, and then others get through easier, right? So that's transmission. We're transmitting X-rays through the body, and so that's what we call transmission data. So that's kind of important to understand as we talk about how CT helps us in nuke med in general. I'll kind of be really brief on this, but a CT system, you've got your computer workstations where you operate the scanner. You've got processing computers that do reconstructions. You've got electronic cabinets that power and run everything. And then you have the gantry. The gantry is the actual scanner, and that's what I'm going to try to focus most on. I'm not going to go as much into the other components of the CT, but going to focus highly on the gantry so you can see kind of how one works. And then we'll get back into why, connecting CT to PET. Oh, and I listed the imaging table, of course. So here's the look inside a gantry. So you've got an X-ray tube. X-ray tube is going to be a little bit beefier than what your normal X-ray tube is on when you're doing just your basic X-rays, because it has to be on for longer periods of time than what you see with X-ray, although that's getting faster and faster on CT. But so you have a pretty beefy X-ray tube. You're going to have collimators. We'll talk about, there's a couple different types of collimators when it comes to CT. You're going to have your detector array, which is on the opposite side of the X-ray tube. And then usually within the camera, you also have a generator for power right on board. So it's kind of your main components. Obviously, there's a lot more in there than that, but we'll mention some of those. This is just kind of a brief, where did CT come from and what advancements? But you had first generation, you have what's called a pencil beam. And you essentially have like one little detector on one side of the patient and the tube on the other, and it would start on one side, it would take a picture, move a little, take a picture, move a little, take a picture. Then that whole setup would move to another angle across the patient, take separate pictures, move again, almost a little more like a SPECT in a way. Then they moved up from this pencil beam and one detector to a fan beam and a detector array, so multiple detectors. And so it did have to move across the patient still, but it made it a little faster. And then you eventually came to third generation, which is mostly what you see today. Here you have a cone beam, and you have a multiple detector array on the opposite side of the patient that's actually curved to match the X-ray beam. And that's what you're going to see most today. Those two rotate around the patient at the same time and continuously image. There's going to be two kind of types of CT scan that are going to matter later when we talk about how a CT scanner works. And so you've got the conventional, which they call axial or step and shoot. And that's where the camera does a slice and then moves the patient through the camera, but the table will move. It does a slice, table moves, slice. So that's your step and shoot. And then you've got your helical, or sometimes called spiral, which is continuous motion of the gantry with continuous motion of the table as it comes through, kind of forms kind of that helical shape, looks like a slinky. And so that's kind of continuous imaging. There's kind of 4 key developments that helped when we came up with those helical systems. One of them is the fact that you can do continuous X-ray tubes. So that's why I mentioned the tubes have to be sufficient to be able to be on for a long period of time, at least longer than kind of your conventional X-ray tube. The other thing that has made it possible for kind of that helical scan is the slip ring technology, and I'll show you a picture in a minute of what that is. And then obviously continuous motion of the table. The other thing that these cameras do is they continuously transfer data as they're imaging. So all of that has made CTs really fast and really efficient. So here's the slip ring. This is what makes it possible for the gantry to kind of continuously move. This slip ring is probably going to be in your gamma camera as well, and it is in a PET. But essentially, I like to compare this. In Salt Lake, they have a light rail system called Trax. If you've ever seen one of those light rail carts, you've got the cart and then you have that antenna that sticks up and you've got wires above, and that antenna contacts those wires, and that's how the cart gets its power. And so as it moves along, it can move freely under there and kind of get power without being connected to something. And so it all runs, electronically. So this works in a very similar way. You have this brush block. So underneath here are a bunch of wire brushes. It almost looks like a paintbrush, but multiple paintbrushes in a row. And those brushes are contacting the ring here. And that's how it's transferring the power. So the power is being transferred through those rings. So no matter how many times that ring spins around, those brushes are always in contact with it, and it can continuously move and continuously have the power. And then the other one down here is it's an electronic. This is what receives kind of the signal and sends the data out at the same time. So this is why it can gather and have power and also send the whole time because of that what they call a slip ring. So kind of cool technology. The other thing to understand, and the reason I bring this up, most of the scanners you're going to see today are what we call multi-detector, which means they have multi-detector arrays. It's not just one single array, it's multiple. The initial cameras, when they first came out with 3rd generation, just had one single detector array. And so the only reason I really even teach you this or bring this up is because as you're studying this chapter in the book, there are certain things that work the way they work on a single detector, and they're different on a multi-detector. And the book doesn't do a great job at separating those two. So I'm going to try to help you clear out that mud a little bit. But just know that there can be single detector and there can be multi-detector, and it's going to affect some of the other things we can do. Now, both of these can be either conventional, which is the step and shoot, or they can be axial helical, right? And so there's a little bit of mud that hopefully I can clear up for you. Here's an X-ray tube. I'm willing to bet that I could ask multiple of you to tell me about this, and you could teach it probably better than I could. So I'm going to be very brief on this. But in your tube, you have a cathode and an anode. It's enveloped in a glass envelope, and essentially what you have here is on the cathode side, you're going to have a little filament that creates a bunch of electrons called thermionic emission. You have a kilovoltage that's applied across from the cathode to the anode. It pulls those electrons over. They strike the anode, and that produces a couple of types of X-rays that we'll get into. Okay, that's about as much as I'll say on it. But I'm sure most of you know that pretty darn well. There's 2 types of X-rays that we need to worry about that are produced by an X-ray tube. Those are Bremsstrahlung and characteristic. So Bremsstrahlung means breaking. It's a German word, and basically that's where that electron comes in, comes close to the nucleus, is pulled by the nucleus, and changes direction. When that change and slow down in direction happens, it gives off X-rays in the form of Bremsstrahlung. It's kind of the main X-rays that come out of an X-ray tube. The other ones that can happen also is when you get a K-shell that gets struck by one of those electrons, that gets knocked out, and then we have a characteristic reaction, which we've mentioned a few times in this class, where the shells will fill their vacancies and give off X-rays as those come off in the form of characteristic X-rays. So there's your 2 types. So what you learn in X-ray, same thing for CT here. We're going to talk about what's called KVP, or kilovoltage peak, and we'll also talk about MA. So kilovoltage peak is the energy, the maximum energy that's produced in the machine. When we think of KVP, we need to think not of amount, but we need to think of penetration power of X-ray. So higher KVPs will push the X-rays harder and can get through body parts better, right? PET uses 80 to 140 KVP. I know in X-ray, you probably about the highest you get is probably like 120 with the chest X-ray, if I can remember back that far. But here you're going to use about 80 to 140 as kind of typical ranges. Advantages of the KVP are you're going to have better penetration through body parts when we have higher KVP, decreased quantum noise, and a reduction in what we call beam hardening artifacts, which we'll kind of mention later. You guys are all going to disagree with me. You're going to kill me. I'm just writing what's on the book here. The book mentions higher dose to the patient, and I know all of your X-ray brains are going to be like, no, when we increase KV, that's better for the patient. I think what the book is trying to say here is if all other things held normal, that you could get some higher dose to the patient. I don't love that. I just listed it for the book. I'm not going to test you on that. I highly doubt you'll be tested on that. Just use your basic X-ray principles, which is that, a good KV is going to get photons through the patient. If we have a really low KV, we leave a bunch of photons in the patient. Trust that X-ray brain, that works fine. The other compromise is it reduces differences in intensity in tissue densities, okay? Then we're going to talk about MA. Now, notice for you X-ray people, I didn't say MAS. So MA stands for milliamperage. And in X-ray, we do milliamperage seconds because it's the time that you have the button pushed or the time of exposure. In CT, our time is more determined by the table motion and gantry motion, and it depends. So in CT, they don't talk about mass, they just talk about MAs, okay? So MA is the amount of X-rays that come off the tube, okay? So not the strength of them, but the amount of them. Usually in CT, you've got ranges anywhere from 50 to 400 MA. We will talk about using something in a lower MA range for attenuation correction and why and how we can do that. The higher number of photons that get through and get to your image, the better image you're going to create that has less noise. If we don't get enough photons through, we won't have a great image. The more you go up on your MA, you're going to increase patient dose. And then, of course, there's a reaction between the KV and the MA, which I won't get into. We're not, again, certifying in CT or reteaching X-ray here. Advantages of higher MA are decreased quantum noise, so you get a better image. You also increase your contrast resolution. And then compromises of higher MA are, of course, the more X-rays we put out, the more dose we're going to give to our patient. Okay. So I want to show you some images here and how those two kind of affect imaging, because that's the main thing I think I want you to understand from a nuke perspective. So this first picture has some what we call quantum noise. You'll just notice that the image is kind of grainy, has this kind of grainy look. And what we've done here is you've got 80 kVp, so that's your push, your power through, and then 200 MA. So what this situation here, what's happening is you've got enough MA, you've got enough photons coming out. You just didn't give them enough push. So what's happening here is a lot of those photons didn't make it through the patient to the detector array. And so this is bad because not only does the image look bad, but you've increased the dose to the patient because most of the X-rays stayed in the body and didn't get through. So that's a no good picture. We don't want to use that. This next one is a much better in your contrast resolution. It doesn't have that grainy appearance. So this is 140 kVp and 200 MA. So again, that's pretty common range right there for a CT, and that looks beautiful. Down here, you've got what's called a ring artifact. And what's happening here is both have been reduced too small. So you have 80 kVp and 30 MA. So there's not a lot to begin with to form an image off of because the MA is so low, but then the 80 kVp is not getting enough push. And so what's actually happening here is some of the detector array, it's actually not getting enough exposure to get a response from the detector. And so it's leaving that detector blank. And so what happens then is it reforms the image, because again, it goes around 360 degrees. Is you're seeing these rings everywhere where those blank detectors were left. That's what these rings are. It's called a ring artifact. And that's from having too low of not enough getting through the patient, in this case, because really low KV and really low MA. Then the next one is the kind of the opposite of A. It also is not a great looking image. It's sort of grainy, so it's very similar look, but it's because the factors are actually flipped opposite. So instead of low KV, we have a good KV, but instead of a decent MA, we've got a really low MA. So you can get quantum noise there. Now, on a diagnostic CT, you don't want to see this either. However, we are going to use this in Nuke Med to do what we call attenuation correction, and I'll show you that later. And the reason is that for attenuation correction to work, our resolution only has to be as good as either the PET or the gamma camera resolution to do its function. And so we'll talk about what that means later. But this is nice because we can use a 140 kV range with 30 MA. And what we're doing is we're penetrating, we're getting through the patient. It's just we're not giving a lot to the patient. So this is a low dose CT, which we want in nukes because we're already gonna make their body part radioactive. And on top of that, we do another CT. If it's full diagnostic, now we're giving them a pretty high dose. But for attenuation correction purposes, we can do this low dose, and I'll explain why in a couple slides, why this actually works and we use it in Nuke Med. Now, that will apply mostly to, again, attenuation correction. When we talk about anatomical location, which is what you often do like in your cardiac PET, you're probably going to be going closer again to getting a diagnostic looking CT, so for location of cancer cells and things like that. So, and we'll get more detailed. So there's in an X-ray, or excuse me, in a CT tube, there is an X-ray filter. And what an X-ray filter does, or what a filter does in any, you have the same thing in your X-ray tube, but a filter is placed right after the X-ray tube. And essentially what a filter is trying to do is it's trying to get rid of any X-rays that are coming off the tube that are not useful to us. Either they're in too low of an energy range, and we're trying to get them out. Now, what a filter does is it results in something called beam hardening. And what beam hardening does is beam hardening is just saying that of all the energy coming off the X-ray tube, we're gonna want the higher energy ones. So I don't know why they use the word hardened. It's kind of funny, but just think of the harder your X-ray tube is, the higher energy it is, right? Like it's strong, it's hard. And so it's better. So when we cut out some of the lower energy parts of the X-ray coming through, we've hardened up that beam. We may talk about beam hardening artifacts later, but that's the idea of beam hardening. Now, in your X-ray tube, you're pretty much all you're doing with your X-ray tube when you have a filter is just getting rid of that low end stuff that you don't want. There's going to be a slight different purpose in CT, and that's what we'll talk about when we talk about a bow tie filter. Okay, and there's information on bow tie there, but here a bow tie filter. So the filter in a X-ray tube is often either flat or it's angled at the exact angle of the X-ray tube itself, of how the tube is coming out. In CT, it's going to be put like a bow tie. It's going to have kind of this bow tie shape that you see right here. The reason for that, actually, it's this one right here, this bow tie. The reason for that is, remember, in X-ray, excuse me, in CT, we're always imaging in the axial position, right? What that means is that we can always rely on the fact that our X-ray is going to hit our patient in a very similar, in basically the same orientation. So a patient sits, this is to represent a patient here. And what you'll notice on most patients, you're going to have they're going to be thicker towards the middle and thinner towards the edges, right? Now, I understand every patient has a different habitus, and that isn't always exact, but generally your patient's going to be thicker in the middle. So what they've done with the bow tie filter is they've made the filter thinner in the center and thicker towards the outside. So not only are we cutting down on some of those unuseful X-rays coming through, but the other thing this does is it makes it so that the X-ray towards the edge of the body, where the body is thinner, are a little are a little attenuated, and the middle of the body is getting a little bit more coming through. And so you pretty much just, it evens out kind of the look of the patient with that bow tie filter. And I kind of mentioned that right here. Let's see where I put it. Yeah, so right here. So it aids in the shaping energy distribution of the beam, right? So it's shaped in that bow tie, prevents the edges of the beam from being too hard, and for the energy distribution across the field is more uniform. I like the way that says it. That said it a lot better than what I just did, but that's the idea. Okay, and there's where the location of the filter is. Again, like I said, just right after the X-ray tube. This right here represents, this kind of gives you a look at why a filter works really good, is that this represents the number of photons coming off, and this is kind of unfiltered and filtered. And what you'll notice, this is kind of the energy range is, and this would be in kV down here, so like 50 kV, 100 kV. So what you see on here is that the filter cuts out all across the spectrum of kV range. It does cut some out, but what you'll notice in this chart is, look at how much more down here it cuts on the low end than any possibility of cutting anything on the high end, right? And that's what you want, because all of the stuff down here is that unuseful X-rays that don't have enough power to penetrate the body, and all you're doing is increasing dose, okay? So that's the purpose of the filter. Again, it evens out and smooths out the beam so we don't have hardening towards the edges, and then gets rid of those unwanted photons. Okay, so detectors. I'm not going to give you the physics of the detectors, but the detectors in CT are what they call solid state detectors. So they don't function on like the gas or crystal. They're what they call a solid state. I'm going to leave it at that because we don't need to get into that for purposes of nuclear medicine. But here's where you can understand that this is like the single row detector. So you can have a single row, where most modern cameras right here have a multi detectors. And this would be like your Z axis right here. Okay. And so you have multiple detectors in a detector array, and you have some detectors that are kind of a larger size, and then in systems you can have these smaller detectors in the center, and that's used for depending on what you're trying to look at, that I'll kind of mention here in a minute. But that's kind of your two ways that your detectors are oriented. So you often hear people say, how many slices does your PET scanner or your CT scanner do, right? And they talk about, oh, mine's a 64, 128, whatever. I misunderstood this for a long time, but when we talk about that, how many slices does your camera do? We're not necessarily talking about how many detectors there are in your detector array. What you're actually talking about is how many channels, data channels, your scanner has the capability of being able to use separately. So what that means is that if you have a 16 slice CT, it means there are 16 data channels that you can use to gather separate data. That doesn't necessarily mean that you have 16 detector elements here, although it could match. But in many cameras, they have more than the 16 on say on a 16 slice, you had more than 16. Because here in a minute, we're going to talk about electronic collimation on a CT, and that's the combination of those rows, depending on your slice thickness, is going to be determined by what detector elements you choose to use and how you separate those detector elements for the different channels that you have to use. So you can have a bunch of different configurations that work. Okay, so there's three types of collimation, and this is where the book, when I talked about the single array detectors and the multi-array detectors, it doesn't give you the difference, and it's super confusing because it'll mention both types, but they sound like completely different things. So I'm trying to separate them out for you. So we're going to talk about pre-patient collimation, post-patient collimation, and then detector or that electronic collimation. So the first one is the pre-patient collimation. This happens right after the filter, and honestly, this reminds me a lot of your collimator and your X-ray beam, right? Like it shapes where the X-ray comes out of the tube and how big that is, and so it limits the size of the beam. Okay, and so that's really kind of the only thing that pre-collimation is doing. Most of the cameras have this, but not all of them do. So that's pre-patient collimation. So it may mention that, and that's what it's looking at there. Then you have what's called the post-patient collimator, and that is just before the detector. And what that post-patient collimator does is that's going to determine the slice thickness on a single row detector system. Okay, so I would venture to say that most of your CT scanners today, because they're multi-detector arrays, don't have this type of collimation. Okay, well, that's, again, they don't define that, but essentially what this one does is it just determines slice thickness and gets rid of any x-rays from hitting the detector that you don't want to hit the detector. Okay. So that, and I mentioned that in single slice CT, it's thickness. In multi-slice, it's just more of like a scatter reduction, if they even use them. This type right here is the type that would be used in multi. And so you still call this a post collimator. This reminds me very, very much of the same purpose that our collimators have on a gamma camera. So what this does is it's ahead of the detectors, and it's only going to let parallel x-rays coming through hit the detector, and anything else that in this case would be scatter, like stuff going all over from body scatter or whatever, it's going to cut out and reduce that scatter. But it does not define slice thickness. Okay, so the only time the collimator, that a normal type of post collimator defines slice thickness, is if it's a one detector array, one row of detectors. If it's multi-detectors, they just have this kind of grid. It's almost like a grid in X-ray. And then the last one is the what we could term electronic collimation. I hate saying that in this lecture though, because it's not, I don't want to confuse you with, earlier I said electronic collimation and PET. They're totally different things. But all this is collimation that's determined by which rows or which detector elements we choose to use in our system in what we're detecting. So for example, sorry, I didn't mean to hit that. So for example, this system right here, if this was the arrays, well, let's go up here first. So this is 16. So this is a 16, this has 16 detector rows. If this system was a 16 slice, then each one of these rows would get a slice, and that would determine our thickness, and that would be pretty much it. Most systems, they have some thicker detector elements on the lateral sides and kind of these thinner ones in the middle. Okay. On CT, you're going to get a better detail with the thinner your detectors are when you get these small ones, and less detail on these larger ones. But what you can do is you can combine and reduce what you use. So in this case, this one right here, if this represented a 16 slice CT, what they did here is they opened it up, and they're using, and actually, let's see, they're using 1, 2, 3, 4, 5. So they're actually using 8 channels. So this would be like an 8 slice, but you notice you have way more than 8 detectors. So what they're doing is combining detectors together. So on one channel, they combined these 2 detectors together. On the next channel, they combined these 2. On the next channel, they did all 4, which is the same width as 2 of the larger detectors. 4, 4, 4, 2, 2. Okay, so they ended up with 8 slices on the 8 channels, but they used all these different detectors. Okay, in this case, they were using some wide detectors. When they come down here, it's the same scanner, but what they've done is they've inactivated these outer ones, and they've put all 8 of their channels kind of down the middle. Okay, so in this case, they're only using the small detector elements, which are going to help them have more detail on their scan. But again, this is a smaller slice thickness area. So the idea is that this collimates depending on what you activate on your camera, right? And this is the primary controller of slice thickness in a multi-slice CT. This is what most of your CT scanners are going to look like today. They're going to have some form of multiple detector sizes on the array, and then you can select what you want to use and what you don't want to use, and that's going to determine that slice thickness. And we call that detector collimation. Again, I'll try not to call it electronic because I don't want to confuse you, but it's not a physical thing happening as much as it's turning off or on detectors. The other thing to understand with CT is rotation speed. Rotation speed is defined as the time that it takes for that gantry to do one full rotation in the gantry to do a complete rotation. Patient dose is proportional to rotation speed if you change no other factor. So factors interact, but if everything left the same and you did a really fast rotation, it's going to be less X-rays that came off the tube, right? So rotation speed can affect patient dose. So when we get a faster rotation speed, dose is affected. The other thing that's affected is motion artifacts. So the faster your scan is, the less likely your patient's going to have time to move, and it's going to affect it as much. We're obviously going to increase our output. Rotation speed is really, really important when it comes to cardiac procedures, because again, the heart, you can't stop it, you can't hold it still, it's always beating. So the faster your rotation speed is, the less likely that you're going to have motion on a cardiac type image. Common rotation speeds are 0.3 to 1 second. And the table motion of about 10 to 20 millimeters per second are used in like most PET studies. So it's pretty fast. The other thing that you need to understand when it comes to the scanner and how it functions is pitch. So basically pitch is defined as a ratio between how much that rotation speed or the rotation of the gantry and the movement of the table as the gantry rotates, okay? So what that means is that, say that your slice thickness you're using right here, in fact, I think let's see if I give an example here. I'll just tee up here, but say your slice thickness was 10 centimeters, and let's say that your table speed was also going at each time it moves the table through, it's going at a speed of about 10 centimeters. What that would mean is that every time that camera rotates, that these two are going to line up right on top of each other, and that would be a pitch of 1, right? 10 divided by 10 would give you 1. If we stretch that out and we still have a 10 millimeter thickness, but we're moving through at 20 millimeters each time we rotate, then that means that these are going to separate out. And you took 20 divided by 10, you'd get a pitch of 2, so you get it stretched out. If we went smaller than that, we're doing our 10 millimeter slice and we're only moving at 5 millimeters through the table, we're going to have a pitch of 0.5. So that's your pitch. Pitch changes depending on how fast it goes, okay? Now, advantages here are you're obviously going to have, when you do a pitch of 1, you're going to have the exposure coming out of the tube is going to be at a certain, if we compare everything to 1, we say you're getting a certain exposure as the patient travels through. If we increase the pitch, we're obviously moving the patient faster through the table, so we're going to get a reduction in the exposure because the X-ray isn't going to be on as long. But you'll notice here, because we have space in between, we are not getting as many projections to form our reconstruction out of. So here we're getting projections all the way around the patient. You get a certain number because it passes that many times. Here you're going to get less data to form your projections out of. Notice that there's never a part of the body that's missed. If you follow this line, you're always going through the body somewhere, even though it's circling and it's spread it out, but you're having less projections to form. And then if we have a smaller pitch, we're now overlapping, which means we've increased our patient dose because now the patient isn't moving as fast through the camera, but we've increased our projection data. We have much more data to form images. So again, pitch is going to affect how good of an image you can get, and it's going to affect the dose of the patient. Again, lower pitches, higher dose to patient, greater pitches, less dose to patient, but it's inverse with the image data that you can get. And not just, this would be like, if you said this was like your single slice detector, I just put the same thing with multi-slice. It's just that you're going to have your 4 slices going through at the same time. So not a huge difference here, but just think one detector versus many detectors and what that means. Okay, we need to talk about Hounsfield units. Remember that, excuse me, my voice is starting to get its butt kicked. Remember, we talked about how X-ray or CT in this case is transmission data, meaning you send X-rays through the body. The reason you can get an image is that different tissues attenuate or stop that X-ray less or more than others. So areas that are dark on your image, it means because it was thinner tissue and more X-rays got through. And areas that are lighter towards the gray and white scale were thicker body parts, and they stop more of that those X-rays. And that's what we mean by attenuation. So in any X-ray or CT, we have what's called a linear attenuation coefficient. And all that means is that when the detector sees the X-rays coming through, it gives it a value, a number value. And they're very small numbers, like 0.003 in difference. So there ends up being a lot of different values. And so there's in tissue, and so there's a lot of different numbers that represent that attenuation coefficient. Now, those numbers, in some respect, depends on your CT machine, right? Because some CT machines might be, slightly different or slightly stronger or give slightly scatter. There's differences in machines. And so attenuation coefficient values aren't normalized across different equipment. You can't take a number of how much attenuation you had here and compare it directly over here because they're different machines. So attenuation, what they do in CT is they convert it to what we call Hounsfield units, okay? And what a Hounsfield unit is it's the CT number or the attenuation number compared to water, okay? So in the morning when you do your quality control, you have a phantom you put on to do all of your quality control on your CT. That phantom has water in it, or at least one part of it has water in it. If you have different phantoms are different, but you have water in that phantom. What's happening, what you're doing in the morning is you're scanning that water and your camera is measuring how much attenuation is coming across that water. And it's going to come up with its own little, 0.0 whatever number, right? And every machine in your hospital is doing that. Then what they're going to do is they're going to take that number and they're going to say, I know that number represents water. And because water is going to be kind of the same density across no matter where you get the water, you put it on, it's going to be similar. They take that water and they say, all right, we're going to convert this to what we call a Hounsfield unit, and we're going to call water 0. We're going to make water a 0 number. So if you look here, if you have a scale at Hounsfield unit 0, that's equivalent to water. Anything more dense than water is going to be on the positive side of the Hounsfield scale. And anything less dense than water is going to be on the negative Hounsfield scale. And so what they essentially do is take all those attenuation values and convert them into these Hounsfield units. And what that then does is it makes it so that across CT scanners, everything can be equaled out against water. So a Hounsfield unit on one scanner should match the same actual attenuation value as a Hounsfield unit on another scanner. Now, within the scanner itself, we also use Hounsfield units for certain things that we look at, and we'll get into that later. But understand that this is how it measures the scales of density of the different body parts, again, comparing everything to water. So, and there's good examples here, like the heart is like 10 to 60 Hounsfield units, so it would be a little, it's a little denser. Bone is really dense, so you'll have up to like 1,000 to 3,000 units depending on the density of the bone, so they're way high. And then again, lung is full of a bunch of air, right? And so it's going to be a certain density, and then actual air is negative 1,000. So that's kind of what they'll represent is water is 0, bone is up to about 1,000, and air is negative 1,000. So that's kind of your like general Hounsfield scale to know is water 0, air negative 1,000, bone positive 1,000. That'll give you a really good understanding. Now, in terms of image acquisition, this happens the same as the other modalities that we've talked about. You're going to have image data that's acquired. It's going to give you those those attenuation values. So much like we throw intensity values across the matrix when we're doing gamma camera, and we do lines of response with a PET scanner, Here it's transmission data. So it's attenuation values that it puts across the matrix. So where there was attenuation and where there wasn't, you have brighter or less bright spots. But it's going to reconstruct it in the same way. It's going to form projections. Those projections are going to be formed into sinograms, and then you're going to reconstruct the same way with iterative reconstruction and filter back projection. So they work very much the same. But this is just a representation of again, the CTs actually come off at a slight angle. The gantry, the array is angled at that same angle, but then when it actually reconstructs, it's going to flatten that out, straighten everything out, and reconstruct across the matrix in the same way. Okay. And I believe that's what I have here. Oh, the other thing I wanted to mention, when we talk about reconstruction algorithms, image filter back projection and iterative are the same. And then CT has a ton of proprietary projections that are, again, mixtures of filter back projection and iterative, kind of like PET does. They have so many that they termed them, some people call them kernels. And even on a CT scanner, you'll sometimes use different kernels depending on what you're imaging. Again, I don't think you need to know kernels and what they all are, but just understand that we use iterative, we use filter back projection, and then I would just have in your head, like, oh, a kernel. When people talk about a kernel in CT, they're talking about an algorithm that's used to reconstruct. Okay, now the other thing we need to talk about that is CT display, because this matters as you're looking at CT, and especially as you look at different densities of body parts. So I mentioned there's a wide variety of Hounsfield units, right? If you go from negative 1,000 to 3,000, you're quite a bit of numbers in between all of that. So the human eye, when we start talking about displaying, the human eye supposedly can discern between about 30 to 100 different shades of gray. So already you can see that if all the Hounsfield units were displayed in slightly different shades of gray, our eyes don't even have the ability to make that delineation. We can only do like 30 to 100. The other problem on top of that is most displays are often 8 bits of data. And so what that equals, without getting into it, is that you'd have about 256 different intensities of grays that your display can display. So we have this huge discrepancy between how many actual different attenuation values there are, what our eyes can see, and then what our display can even show us, even if our eyes could see them all. So we have to have a way of resolving that so we can see what we want to see on a CT, and so we can take full advantage of how much data is in a CT. So this is where we talk about a window and leveling, and you're probably familiar with this a little bit with X-ray because there's some similarities here. But in this case, it's all defined on the Hounsfield scale. And so basically what you have is that you have the Hounsfield scale. Again, you can see that here vertically going from negative 1,000 to positive 3,000. And then your display will actually allow you to take a window, okay? And what that does is it takes all of those values of attenuation are represented Hounsfield-wise here. Your display can represent a certain amount from white to black. It takes all of those 256 shades that your display can do, and it displays those on wherever you have your window on your Hounsfield scale. Okay, so what that means is right here when it's in 0 and we're doing water, if we need to look at a body part and represent a bunch of shades of gray on that body part, like let's say a heart that might be somewhere around 30 to 60, we move that window to where that heart is 30 or 60, and now just those Hounsfield units only, that small amount of Hounsfield units, is represented by all 256 shades of gray on your monitor. Now your eye can see some of that, and it can look at that heart with that variation of shades of gray. If I needed to look at bone, I'm going to move this window up here closer to where a bone would be. And now all those 256 shades of gray are represented in that small amount of Hounsfield units. Same thing if I was looking at lungs, I would come down here closer to the negative 1,000, right? And I'd be able to view the details of that lung would show up because I would have all these shades of gray from white to black in that small window. Now, the other thing you can do when we talk about windowing, we're saying we're moving the window along the Hounsfield units, but you can also do the window width. So we can actually make that window really a little window, or we can make it a big window, depending on what we're wanting. But remember, whatever we do, it's going to represent 256 shades of gray within the size of the window and the window placement along the Hounsfield unit scale. Okay. So let me give you some examples of what's happening here. This scan is the exact same scan. It's not a different scan, even though it looks like we're looking at different things. It's the exact same scan, but it's put into a bone window, a lung window, and an abdomen window. Okay. So what you'll notice here is that when we're in the bone window, the lungs are very darkened out. Like you really can't see much, you just see black. But you can see the details, the cortical parts of the bone. You can see these bones in really good detail. And so that's because all those gray shades are more towards where the bone density is at. And so it allows us to see it well. Whereas when you go over here to the lung, the bones are completely whitened out. However, look at this. You can see all the bronchioles. You can see the lungs really well because, again, we've lowered that window down to the Hounsfield range where it's in the negatives. And then an abdomen is going to be somewhere kind of in the middle. We don't want to have it detailed for bone. And so the bone doesn't look great. You can see it, but you can see, like, you come down here and you can look at the liver and you can see things really a lot better. So again, the data in your CT, it has all of this data in there, but it depends on what window you choose. And that's a factor you can look at and change on your CT. You can change these different windows and look at them, but the data exists, right? And so that's going to depend on what you're looking at. And same thing with you're doing your PET. Like if we're looking at a heart and we're using a heart for our attenuation correction and for those things, or we want to look at anything like that, we can put it on that type of window. If we're looking at oncology, we can put it on that window. Depending on what they're looking at, the doctors can change this, but it allows us to see the full range of the actual density differences within a CT scan. So artifacts. I'm not going to go over tons of them. Like you would need to know lots of different artifacts for a CT course, but I'm going to kind of just be general here. But an artifact is essentially anything that causes a discrepancy in the pixel values measured in the study. So something that it measures, right? So, and the three primary sources are just obviously the operator can do something wrong, and that would be, again, like we've done the wrong MA settings or whatever, and we don't have enough to get a good pixel value measured. Could be something's actually wrong with your scanner, and then obviously the patient can cause artifacts with motion and moving and different things like that. Quality control for a CT. I've listed the Joint Commission and the ACR, and there's some things that are required by those organizations that we have to do, and then there's other things that your vendor will have you do depending on your camera. So I've kind of listed the general ones. You obviously do a daily X-ray tube warm up. If you don't warm up your tube, you can crack the tube, and then your system's down. You're obviously going to image that phantom. One of the most important things there, again, is you're imaging water so that you can have your accurate Hounsfield units. And then there's other general system calibrations that it does. Again, I would understand kind of this water phantom idea, but I don't know that you're going to be asked CT quality control questions on your, not my test. You might be, need to know that you should daily warm up your tube and daily do your phantom. But other than that, you don't need to get too detailed on the CT side. So this is a combined PET CT image. You've got the CT data and you've got the PET data, and then here's them combined. I don't know about you guys, but like I think this is cool. If I saw this when I was 8 years old, I would like wigged out and thought I was like in Star Trek or something. I know I'm a nerd, I know, but this is pretty cool that we can combine and we can see such good detailed anatomy and then be able to see actually physiologic process happening within that anatomy. Anyway, PET CT is just, it's awesome. Okay, so that was like, there's your anatomy location, right? So that's one of the main reasons we use PET or CT and PET for is an awesome anatomy localization. And like I mentioned, you're going to use a regular old good quality CT when you do oncology, especially because you're needing to locate lesions and look at things that way. And that's what this represents. The other thing we need to talk about is attenuation correction. And if you guys need to go, you can. Sorry, I'm yakking on too long here. So attenuation correction is required in PET in order to correct the different distribution of the radio tracer that's represented in image. And because the body parts, again, I mentioned we have different density of body parts. You make a body part radioactive. Let's say you're looking at a heart, and let's say you don't image with the arm down, but if you were to image with the arm down, you've got this big body part in the way of those gamma rays making it out to your image, right? If you're especially for female patients, you could have breast tissue that can get in the way of looking at a heart. You can have, if you're looking down in an abdomen for oncology, you can have some patients that have really big adipose tissue, and that can cause problems in how much of your gamma rays get out to your detectors. Okay, and so attenuation correction is something we're going to use to help correct for that. So let me show you. Let's kind of describe the principle here. So what graphic A is supposed to represent is a patient body part, and they've colored kind of this darker part in the middle and the lighter part on the outside. It doesn't necessarily define here what you would say is your PET data, but let's just, for kicks and giggles, let's just say that our PET data is this kind of light color, and then we have something here we're getting less PET data there, right? So let's say we have something in the way. There's some body part right here. So what they'll do is they'll take the PET data, which is what A represents, and they lay that PET data. B represents the PET data being laid over the CT data. Now, because it's transmission data, we have CT, we have Hounsfield units, right? We know how much each body part is thick based on the attenuation of that body part. So what will happen is you take your PET scan, those CT values, those Hounsfield values are laid over the top of that CT scan. And then what happens is the computer looks and it says, anywhere where I see a thick attenuated value based on that Hounsfield unit, I'm going to correct by adding activity, radioactive activity, right? Our image, our emission data. I'm going to add more emission data in that section. And so it looks for those attenuated areas and corrects that. And so when you get to your final image with those two laid on top of each other and those attenuation values corrected for, you're going to get a nice smooth image that actually represents what you looked at, right? So that thick body part that's attenuating part of the radiation is now not attenuating anymore. It's out of the way. Okay, so that's what attenuation correction does. It takes the transmission data and corrects the emission data based on the transmission data. Any questions on that? Now, I mentioned earlier, this is why we can use a low dose, because our resolution of the CT only needs to be as good as the resolution of the PET or the gamma, either one. And so we can use a low-dose CT that looks kind of grainy and modelly because, again, we're not trying to make a diagnosis on that CT. All we're using it is to get sufficient enough Hounsfield units that we can then correct the emission data that is in our PET or our gamma. Okay, so that's great because then we can have less dose on our patient that we give based on a lower amount of MA coming out of the machine. The other type of transmission that is done also that they used to do with CT, or excuse me, used to do with PET, is they would actually have it was usually germanium. It was a source that came out in your PET scanner. And this was before they had CT. They would rotate that germanium source around the patient. And what that would do is it would actually give them transmission data because it's a nuclide that you're using, but they're transmitting it through the body by rotating it around the patient. So similar to a CT. And then they would take that transmission data and use it in the same way to form better images that you could look at. Now, most cameras don't use it in that same way anymore because, again, we've got CT and it's much more efficient, works better. But this is actually images from using that type of transmission data. And what you'll notice, if you think about this, especially in oncology, you give you give patient F18, and it's FDG, which is a radioactive sugar. The G part stands for glucose, right? So you give them a radioactive sugar. Most of your body uses sugar, so that when you give a person FDG, it generally distributes through the body. However, on areas of activity, it gathers more, right? Because they're highly active and they're using that sugar. But you have to think about the fact that we're using a 511. So notice on this upper one, this is a non-attenuated corrected. You can see that this arm like is kind of really hot. It makes it look like there's a lot of activity there. Up here near the shoulders, there's a lot of activity. It actually looks like the lungs, like you can see them really good. They're kind of lit up a little bit. And so you have to ask yourself, like, is this activity? What is going on here? What's happening here is that because your arm is a thinner body part, that 511 gets no attenuation and it just comes right out, and it's going to be seen hotter on the camera than an area like the spine. If you look at the spine, it makes it look like there's hardly any activity in there, but because it's a thicker body part and it has to travel through the rest of the body to get to the detectors. And so this was the primary problem you had with both gamma and PET, is that you had this attenuation going on that made it look like some parts were hot and some parts were not. This one is a transmission data, and this one's done with not CT, it's done with gallium, but they added the two back together and look at those same parts. Like look at the forearms here. They've really evened out. Look at the lungs. The lungs are now represented like they should be, which is not much activity there. Those areas in the shoulder have gone away. The spine actually looks, you can actually see it. It's not just kind of whited out. And so they used to do it that way. Now, again, like I said, with CT, it's done mostly today, but they used to use a radioactive source to do the same thing. This is just a quick, for example purposes, a quick attenuation case study, I guess you could say, that really made a difference. So in our cardiac, we'll do attenuation and correction CT, and then we'll do the perfusion. At our facility, the way it works is on their way into the camera, they'll do a resting CT. We'll do the resting PET, we'll do the stress PET, and then on the way out, we do a stress CT. So we actually do two CTs, one to go with the rest, one to go with the stress. On this particular patient, we got them done, we pulled up images, and I'll go to the first set of images here. What we noticed, and hopefully, and if some of you haven't had a lot of experience with heart yet, we'll be going through more detail next semester, but what you can see here is it looks like on the rest scan, so these are the rest slices here and the stress slices here. The rest scan looks pretty good, and it looks like we're getting perfusion throughout the myocardium. And then you come up to the stress scan, and it looks like kind of this anterior side of the heart is getting pretty good perfusion, but this inferior part of the heart looks like it's reduced quite a bit. And so when we looked at our pictures, we were like, oh shoot, this looks like it could be a positive scan. And we were looking at that, and we were gonna have the patient talk to one of our doctors and go with everything. But we have a bunch of other ancillary data that you get with PET that can point to whether or not the patient is actually having this issue. And all of the ancillary data, and I'll talk about more of that next semester, but all the ancillary data was pointing to this being fine. But yet our pictures were still looking like there was this missing area of perfusion. And so we were scratching our heads and we couldn't figure it out. We're like, what is going on? And so we decided to actually look at our CT scan and see what was going on with it. So if you go back over to the CT scan, you can see, if you go down to this inferior part of the heart, and hopefully you can see it on whatever device you're looking at, but you can see this streak that comes across the bottom. In fact, there's multiple streaks in the CT image. And hopefully you can see them good. If not, blow it up on an image if you're looking on your phone. But you can see these streaks. And what that is that's the motion artifact. And so the CT scan had motion, and it made it look like some denser areas and some lighter areas where they didn't actually exist. Well, then we were questioning, well, is our attenuation correction being affected? Because again, it's based on seeing accurate transmission data. So if your transmission data has issues and problems, it might not be accurate. So what we did is we took the stress perfusion, and instead of marrying it to the stress CT, which is this one here, we actually married it to the rest CT, which didn't have this error. And so let's look at what happened when we did that. So here's our original image where you can see some perfusion defect in that inferior wall. And here let's see, is this right? Oh, here's what I did on this one is I just took the two stresses, so I compared them directly. So here's our original stress with that inferior wall defect, and now here's our stress after we married it to the rest CT. What you'll notice is that perfusion totally filled in. And that made sense with the rest of our data that the doctor was looking at, saying this doesn't make sense. I should be seeing all this other stuff going on. And it's because of that CT error. So again, this is where CT artifacts, CT can make or break, but you have to think and pay attention to the CT to make sure it's also quality CT, that there's not errors, that there's not artifacts, problems in the CT, because it can affect that attenuation correction. So kind of crazy. Here's all three of them compared. So here's my resting scan, our first stress scan, and our second stress. Well, I shouldn't say first stress scan, but our stress scan married to the stress CT, and our stress scan married to the rest CT. So again, pretty cool, pretty different. Okay, one other thing that we need to cover that's kind of an error or something inherent in the system that you need to understand with PET is called the partial volume effect. And what I want you to look at on this graphic, this graphic would represent your crystals, right? So this is like a 5mm crystal. And then what these would represent, what we'll call them for this purpose is, let's just say they're lesions, like you're looking at an oncology PET. And these are different sizes of lesions, okay? What happens is there's an inherent error, or this is what we call this volume effect, that can happen when the size of an object that you're trying to image begins to approach the resolution of the imaging system. Remember, I mentioned the resolution is determined by the size of the crystals. So what you're going to have is that when a crystal sees activity, it's going to just take whatever it sees, and it's going to average that out and make it as an area of activity. So what do I mean by that? In the center of this big lesion, you're seeing all these ones in the middle that are completely covered by that anatomy, right? The anatomy is showing up right over it, and you're seeing it's going to fill all those in, which means that this pixel or this crystal is going to take the average energy of that photon and represent it as it goes in the camera and represent it as your line of response. However, you notice as we get out towards the edges of this lesion, you have much more of this crystal being covered by no activity versus a little bit of activity, which means because this crystal can't separate itself, it's just going to average the activity it sees in here, which means the center of this lesion is going to look a lot more like you have a lot more counts, and it's going to be brighter on your image than towards the edge of this lesion. And so how that causes a problem is as you go down the scale in size, you start to get to this very small one, and what you're going to have is you're going to have none of these crystals are going to see the full size activity of this particular lesion because of where it's located. So you're going to have a averaging here and averaging here and averaging here and an averaging here. So the intensity of this lesion isn't going to show up as intense. And then of course the resolution can be reduced as they get smaller and smaller. That's why your resolution is really limited to the pixels that you, or not the pixels, sorry. They say pixels on here, which I don't like, but the size of your crystals. This is what I was talking about. So there's a phantom called a JSAC phantom that you can use with PET, and it's got little spheres inside of kind of a tube, and you put radioactivity in those spheres. And what you'll notice is here, the same amount of radioactivity is actually in the distribution of these spheres. But what you notice is that these large spheres, which again would be all these I keep saying pixels, all these crystals representing seeing that particular activity, you notice they're nice and bright and pretty well defined. As you get smaller in this phantom, you notice that not only does the resolution get harder to see, but you notice that there's a dimming effect, okay? And that's again because this partial volume idea. So there's this dimming that comes. So understanding that is important, that your PET scanner does have limitations on how small of activity areas it can see, again, limited by the size of your crystals. The other thing we need to talk about really quick is, and this is what's really advantageous about PET, whether you're using it in cardiology or whether you're using it in oncology, is that you can get quantitative data. What we mean by that is that in PET, we can look at the uptake of tracer and we can quantify the amount of that tracer that is in a particular body area. So for this example, in the case of oncology, quantitative data is read in what we call SUVs, which are standard uptake values, okay? This is calculated by taking the ratio of concentration of activity in a region of interest that you or the doc or whoever makes compared to the injected dose that you gave divided by the body weight. Here's the math equation of how that would be, an SUV would be figured out. I know this sentence is weird. It's like, wait, what did he say? So let me try to describe it like simpler. When you give FDG, remember that it has glucose, right? And so you give FDG into the body, all portions of the body are able to use glucose. So you're going to have a somewhat even distribution across the body, with the exception again of the cancer cells, because they use high glucose, they're high active, they're going to pull in more glucose depending on how active they are, right? And so what they're doing then is they're saying, we know how much we injected, we measured how much we injected, and it's going to be this ROI, this activity, so we can circle an ROI, and we're going to divide that by how much we injected. We also do body weight. Body weight represents the distribution across the body. So essentially what you're saying when you do an SUV is you're like, okay, how much is in here compared to what I expect on an even distribution across the body? And that's going to give you your SUV value, okay? And what that says, like right here, ROIs calculate counts per voxel, which is translated into activity concentration of millibecquerels per kilogram, okay? Now, I know we don't use becquerels very much, but that's what I'm trying to help you see, is that it's doing it per quantity of tissue. And that's why when you do a PET scan, you need to get the time of injection, because we need to know what the dose measured, because it's going to calculate it based on dose. And then it's really important to get the accurate body weights. Some places will do like height and weight and calculate it by those factors, which is basically like BMI, right? And so, but it's going to be either BMI or just body weight straight. But that takes account for the distribution, what the distribution we expect to be in this type of body compared to then what is actually distributed in this area of high uptake and high counts. And what that allows you to do then is just get a quantitative idea of how much is there. And the reason this is so important, again, is because when you're working with cancer patients and you do a PET scan and we detect cancer, they're going to go away and they're going to have treatment and they're going to have some things and they're going to come back. And the question is, how is the staging of this cancer going? Like, is this effective? You can look at an image and be like, well, I mean, there's still an area of activity there. But if you're just looking at images, you can't actually say, well, how much activity is there? How active is that cancer area? Whereas with an SUV, when you circle it, it's going to take into account, again, the actual counts of that area based on the body weight and the dose that you gave. And so it allows us to get quantitative value out of that scan. Again, that's why it's important when you're doing a PET that you're measuring those things beforehand so that you know exactly what the time, the dose, and the patient body habitus or weight or whatever you use at your facility, okay? I'll show you one other area that we use it in quantitatively in cardiology. So we do a couple of different types of scans besides just the stress test. But this one I'm going to show you right now is inflammation. So we can detect inflammation within the cardiac tissue. Inflammation and perfusion issues can mimic each other. So if we do a perfusion scan on a patient, we see an area missing, typically that's because of some obstruction in the coronary arteries, right? And in that case, we're talking about coronary artery disease. However, inflammation, what can happen is if you have inflammation within the actual tissue, the pressure of that inflammation can push on the vessels within the heart, and it can make it so that less blood flow can get to the area of inflammation. Okay, so they're usually reduced in blood flow, which on a stress test can look and appear like a perfusion defect from some kind of blockage. And so an inflammation study allows us to determine the difference and then quantify amounts there as well. So what we do with this scan is we give normally the cardiac tissue prefers fatty acid as its mode of metabolism, right? So it loves fatty acids. However, in an area where you have low blood flow, you're going to have low oxygen, and oxygen is needed to metabolize fatty acids and break it down. Less oxygen is needed to metabolize glucose and sugar. So what we do is we have the patient eat a big meal of fatty acids, so no carbohydrates, but like bacon and eggs or whatever for their last meal, and then they fast. And what that does is it takes all of the normal tissue that's not inflamed and it gives it a big dose of something that it likes. Fat and happy, it's satisfied. Then what that allows us to do is come in and inject FDG. And because the area of inflammation is low blood flow, it can't accept and metabolize that fatty acids. So as soon as you put that sugar in there and the body's been starved of the sugar, it's going to gather that sugar up, right? It's going to eat it up. And so that's what you're seeing here. So here's an image, and you can see this kind of lateral wall of the heart is lighting up here with FDG. And so we're asking the question, it looks like from this scan that we have some inflammation. Now, what we do here is we'll take the PET CT, which is what you see here, and we'll do some quantitative data and we'll do some ROIs. And in this case, the standard that they have to qualify a positive test on inflammation is that it has to be twice the background. Okay, so in this case, what we do is we use the liver as a background, and then we do an ROI over that hot area. And if it's at least twice as hot, then they will consider that inflammation. So go back to this scan. Again, if we just looked at this picture, we'd be like, oh, there is a hot area there. Like, is this inflammation? What's going on? We go over here and we actually get values. And if you look at the value here, the mean value SUV value, and this again is by body weight, you get 1.92 on the liver. So it means there's activity going in the liver, and you get 2.48 on the heart. So this technically, based on quantitative data, doesn't qualify as inflammation, even though we do see some increased uptake. Now, a doctor reading this, could they make some decisions? Sure. But in terms of quantity numbers, they don't have the numbers to back them up on, and for sure calling this positive. On the next one, you'll see that there's another scan where we have these two hot areas, kind of one at the apex and one at the base of the heart. And when we did the SUV values on those two areas, our liver came up as 1.98, and then our hot area came up as 4.06. So this would be enough to qualify as inflammation, again, based on that quantitative uptake. Okay. We did a couple different pictures of those two. That's the one at the apex. That's the one up near the base. So again, really cool stuff that you can do with PET and with being able to have these standard uptake values that you can use. Okay. Just got a couple slides left. So I just wanted to mention displaying PET data. Typically what you'll see, it can be a challenge on how to show as much data and volume as they have and be able to make, especially with oncology, be able to, one of the things in oncology that's super important is locating, not just quantifying areas of uptake, but also locating where they're at, right? And so the way they display PET data that makes this so efficient and awesome is usually you'll have PET data supplied in an axial, coronal, and sagittal views. And usually you'll have a screen that can be done at the same time. And then you have location, you have reference lines. So you'll see these lines, and you can move these reference lines to hot areas of uptake. And what it will do is allow you to view all of those things in all the planes at the same time, which again, we can't really do with just our normal spots on if we were looking at a bone scan or something like that, we can't quite do this kind of location. And so PET allows that. You can do this somewhat on SPECT, but again, usually don't get quite as good of images on SPECT. And so this is another kind of advantage, is the ability to display the PET data and use for localization in the way that it does. Last thing we'll talk about real quick is just some quality control. Quality control kind of has two headings: the characterization and corrections or calibrations. I've kind of highlighted probably the two that are done daily, and that's mainly what you'll need to know. The rest of these are usually service engineer, and they happen, quarterly at different times. But just kind of give you a quick explanation. So energy window, makes sure, all that it does is it makes sure that the camera is set to look for 511 keV photons, right? That's done by a service engineer, but again, we change our energy window on a gamma camera, right? You can change it depending on what you're looking at. In this case, it's nice because we only need to look for 511, because if it's not 511, then it isn't PET. So if we have an energy window calibrated to only look for that, that's going to right out of the gate improve our images. Even if we end up with some slight scatter and things like that, we can tell our window we only want to see this. And so that's an advantage, and that's calibrated on a quarterly basis. The gain settings they're done with the photo multiplier too when we talk about gain. And what it is it ensures that the amplifiers, which provide power to each photo multiplier tube, are uniform. So there's a radioactive source that goes into the camera. The camera knows its activity, and so it knows what it expects to see on each photo multiplier tube, and those should be even. And then what it does is it compares what the photo multiplier is giving in its pulse at the excuse me, I can't think of the word on it, I just said it. Oh my gosh. At the amplifier, sorry, it's getting long. Compares that pulse that it gets at the amplifier and then evens it out so that all of those PMT tubes are reading at this, at the same intensity and same gain setting. So that's what that is. Coincidence timing window just adjusts for timing differences in the circuitry that controls the timing windows and the seeing events, again, done by an engineer. Then your blank scan is one that you'll probably see the most, and I believe on the one of your things you have to pass off as a blank scan. I always thought that was kind of funny because it's really basically like it's almost like your daily flood for a PET scan. But there's a phantom that you put into your PET, and it puts out transmission data, and then all of your scan basically performs very much similar to your floods. It looks to make sure that all of the detectors that are 180 degrees apart are seeing the same thing. So whereas on your flood for your gamma camera, it kind of just equals everything out. On a blank scan, it's specifically looking at 180 degrees apart channels and making sure that they see things the same. And then it normalizes that across the whole entire scanner and all the rings of detectors. Normalization is kind of like your high count floods, kind of the same idea. It's done with a rod source. It's a long acquisition, like sometimes a 24-hour acquisition. So usually this is done by like a service engineer, but it's going to measure, again, similar to the blank scan, but this one is going to normalize what it sees so that all of the photomultiplier tubes and crystals are reading similar values, again, based on the fact that it knows that phantom is a certain activity. And then the last one is absolute well counter or absolute activity. They call this well counter calibration sometimes. I don't love referring to it as that because then it confuses you with the well counter. But it's basically what checks for the accuracy of SUV values. And so it takes a water-filled phantom with a known volume and a known activity. So you'll put a certain activity in it. And again, some places I've seen do this and some places don't, but the volume of the water is known, and then the activity you put in is known. And then basically it's scanned and reconstructed, and it'll basically just try to do any correction that's needed for SUVs. Because again, it should know what the SUVs should read on all detectors. It should be even. And so it will take that water phantom and it will equal out and make the SUV value numbers accurate and correct. It's kind of like, it's sort of like scanning a water phantom to get your Hounsfield units. Kind of a similar idea, but not quite. So hopefully that doesn't confuse you too much. But here's what a blank scan looks like. So I don't love this image either because this blank scan is really, really long because remember, it detects all those different lines of response across two different buckets. And so when you look at this on your scanner, and maybe some of you have seen this, maybe not, but ask your tech to look at the blank scan after you do it. So this actually is like, it's almost like something you can scroll through. So if I were to go down, if there was a little scroll right here, it would scroll and scroll and scroll and scroll. Like, so this thing is like really, 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 really long. It's not just this size that you see here from here to here. It extend way down, way further. And so usually on your camera, you can go through and you can scroll through and you can look at all those. And so that's what we're seeing is this would be like a bucket from one bucket across to the other, like a line of response. So that's what you're seeing. It represents the camera and all those lines of response. So in this one, it's basically showing one is out. Something's wrong with one of these buckets that it's not detecting a 180-degree line of response. Radiation safety in PET, I mean, it's really the same. The only difference is a lot of your PET things will be thicker values. Most of your attenuated materials, lead, all that kind of stuff is going to be thicker. One of the big differences, for example, in like your syringe shields, usually they use tungsten in PET because we have to account for blocking that high energy photon, the 511. And so obviously you're going to want to limit, especially oncology where your patient circulates for a while. You don't want to be hanging out with them and talking to them and shooting breeze. Like you want to get away. All the radiation principles apply, but I would say that for you, in terms of radiation safety, like staying away, distance is going to be your number one thing. Like the little amount of time that you need to be by that by a 511 keV is the better. And so stay away from your patients. Only handle it when you need to. Make it fast and be done with it. That's why I put on here. Distance is most effective. And I think that's it. You made it. So sorry, I went way longer than I thought I was going to. I'm gonna stop sharing and then any quick questions. I'll probably just let you guys get out of here so you can get back to what you're doing. But finish your tests, finish your reviews. Remember, I gave you till the 13th of December. If you have questions, please contact me and let me know what you need, what's going on, how I can help. All right, I'm gonna end it.
Wait.
Oh, go ahead.
Okay.
There are questions.
Yeah, so I have one question that's to do specifically with my clinic, but then another question about scanners. So
Okay.
we're getting a new scanner that my techs like to call shark teeth. It's where each of the individual parts come in and move, and it's gonna be our PET scanner. So instead of being like a solid circle, each parts of the PET are going to be individual, so it can more body contour. How does that work with the like the 180? Like, because the crystals aren't going to be all connected, right? Because they're going to be in individual little
Interesting.
things that come in.
I'm gonna give you a big fat. I don't know, Ashley. I've never even
Okay.
heard of that. I'm gonna have to
Okay.
look at that.
Yeah,
Huh.
our scanner's really old, so we're getting a new one. Our scanner's probably 7 to 9 years old, somewhere.
I wonder if they come in. I wonder if things come. Yeah, I don't know. That is weird. But it's a PET scanner, huh? Huh. Okay, I'm gonna look it up. You gave me something to look up. I have no idea.
Okay. And then on a totally separate note, it's been about 3 years since we've done a vitality scan. So our department's protocol is to use like the glucose drinks to get them within the correct range to do like an FDG for the vitality scan because we don't have a rubidium generator. And then they don't do thallium anymore. But a couple techs I've heard of like using nitro and tech to do a vitality scan instead. Are there other vitality like protocols you've heard of?
So I think you're talking about a viability. Is that
Yeah.
right? Viability scan? No. So we use the glucose drink. So real quick, that the idea with the viability in terms of at least using the glucose is you're trying to change. It has to do with the substrate use, like we talked about before. Like the heart prefers fatty acid, and so you've got to get it to crave glucose instead. So the best way I can describe this is going to sound funny, but it's kind of like this is going to sound so bad, but the crack dealer on the street, right? Like he always gives you the first one for free, and then he takes it away and says, "Well, now you got to pay." So that's what's happening is the cardiac tissue, you starve it from anything else, and then you give the sugar. And what you're trying to do is get the cardiac tissue because it's been fasting from everything else. You're giving sugar, and it's like, okay, fine, I'll take the sugar. I'm super hungry. That's what the glucose drink does. you're getting it to crave and you're getting everything to switch over to sugar. And then what you're going to do is usually you give insulin and you bring it back down and you take it away. And essentially you're just creating a sugar need so that when you give the FDG, then that craving of the sugar is really, really strong and it's going to pull that in to any areas. Now, because also the same thing with with a viability, what you're questioning is usually it's an area that's been infarcted or they thought it's been infarcted, so it's been super low blood flow for a long time. And so again, it has a hard time with fatty acids in the beginning. But yeah, you're trying to crave sugar, reduce sugar, and then get it to crave the sugar and take it in again. And so usually on a viability, you'll see the heart. A lot of the heart areas will get it. It's different than the one I described, which is you'll only see FDG in the area that is is inflamed. With this, you could see it throughout the tissue, but what you're looking for is you're looking for an area that previously wouldn't fill in to fill in by getting that sugar to crave. Now, as far as the other nuclides, I don't know. I haven't used them, but I don't know if that answered your question or not. But
yeah, I just didn't know if you had heard of any other protocols. Like I said, we haven't done ours at our clinic in over 3 years, and so they're all scrambling to try to find what protocols they can use since we don't have rubidium.
Yeah, you're gonna. I mean, you can. You technically could do the what all rubidium does is it gives you normal perfusion. So you first want to verify before you do a viability if there's even a defect, if there's even a missing portion. If on the perfusion you do because usually what you should see is you should see a rest that has a defect and has an area of missing perfusion, and then you should see a stress that has a similar missing area of perfusion. And they should know that. They're like, okay, well, because the question is that tissue dead, or is it what we call hibernating myocardium, which is myocardium that's just been so low in blood flow for so long because of multiple infarcts and things that have happened that it is alive, but it's really low blood flow, right? And so you should have that. So you could technically do a SPECT and determine that, because if I pull up that image and I do my resting scan and my entire heart wall fills in on the rest, like, you don't need a viability. You're done. You just prove that it's there, right? If you do a rest and a stress, you want to verify those two areas are both having an issue. And that's the purpose of the perfusion. So the only thing you need rubidium for is just to verify the perfusion before you move on to trying to do a viability. You could do a SPECT with tech, verify that, and then just go straight to the FDG part for the viability.
Yeah, I think that's what our protocol calls for. We've already done a rest and a stress on this patient. So yeah, now they want to do the viability.
Yeah, so I would argue that you don't need to do a PET scan. I mean, it's better imaging, more detailed. It's nice to compare a PET to a PET, but all you're really wanting to do in that first set of images is confirm, yes, there is an area that we're questioning if it's just hibernating myocardium that's missing. That's it. So, yeah. Okay. Jesse, did you have something? Are you done, Ashley? I'm assuming. Sorry, I shouldn't assume. Yeah, go ahead, Jesse. Oh, you don't. Okay.
Yeah, I've got nothing. I was just listening.
Oh, okay. I thought I saw your hand. Okay, cool. All right. I'm gonna end it. I gotta get my butt to work. We'll see you guys later. Again, contact me if you need me. I'm gonna end it.